base. This comes under the microchip, microcontroller, then digital signal processor. So day by day, the semiconductor industry is evolving, and some digitization, some microcontroller base is happening infrequently actually, and that's why the electronics industry is growing fastly. Okay, so with this, we need to have evolve the semiconductor material. So previously, in traditional way, we are using the silicon actually. Silicon as a material for the some making of the chips or some integrated circuits and controllers, digital signal processor and all. But some of the limitations, see, once system is there, they have some pros and cons actually. So mostly in that, the traditional silicon, we have the low cost effective solutions. Then usability point of view, it's wide globally used and it's available quickly. So that's what till the days, the silicon is mostly popular in the industry. But some of the range, if currently, if you are going for industry is moving towards the some high frequency applications, some time bound applications, some mission critical applications. So in that case, we need to have some additional advanced performance actually, and advanced performance, then advanced efficiency when we are using the electronics in our chipsets actually. So that's what this silicon carbide is using. Sorry, silicon is using in previous one. Now the thing is added one is a silicon carbide and gallium nitride, which is the current solutions in this in future actually. So why advanced material we are taking as advantages in our automotive applications? Mainly, the automotive industry is coming as future solutions like what I am working, and I have the expertise or experience in the electrical vehicle domain, then SDV, then ADAS features, then autonomous driving and all. That's what we required HPC, high performance computing, and for this high performance computing, we required some hardware as a high hardware capability to execution of this instruction as per this number of instruction, and very high in the terms in this software executions. And in terms of the software, we require capable hardware for that. So that's what we required, this silicon carbide and gallium nitride. This is the performance, and again we need to have some, we required for efficiency, because in EV, if we are considering electrical vehicle, we need to use the effective power electronics to utilize our battery power to this our motor, to maintain the battery health, as well as the battery means reduce the battery power to utilize the full of efficiency of this vehicle and increase the range. That is our main motto for the using this advanced advanced semiconductor carbide and gallium nitride actually. So that is the use. This is one two basically for semiconductor. One is a silicon carbide, and they have some different properties. See, in the silicon carbide, basically we have the wide band gap, and mainly it's focusing on the efficiency part in the silicon carbide. But if we are going for the gallium nitride, if high voltage application, like in industry, we are going for the high voltage 850 DC or 750 DC, 800, 700, then we are using the 400 volt DC. So in that case, we require high voltage handling applications also, in terms of means in terms of our semiconductor power semiconductor also, like our power board in using the driver boards and all. That is the main point. And one point is that time constraint. So if we are going for this advanced material, we have some high efficiency and high resolutions also, means high sampling time, we can execute our internal topology. So that is the material we are using as a industry applications. In terms of we are saying this presentation as advanced semiconductor in this power electronics application in the automotive. Why? Because of in the EV application, electrical vehicle application, we required inverter and traction motor control, then onboard charger, DC to DC converter, as well as we required battery management system. So in that, how we are using this power electronics component? This is power electronics component. Basically, DC to DC converter and onboard charger we are using for charging the components, and to utilize effective utilization of our grid grid supply to power factor correction, and then we are providing to the battery charging. So uh, in that MOSFET and some IGBTs and power electronics is included basically in the power board. And inverter also we have three legs controller basically to converting this battery supply to the motor actually is DC to AC. So in that also power electronics is included. So in that power electronics included, we need to maintain the efficiency. That is a critical factor in the power electronics. So by using this material, we can utilize this wide band of this silicon carbide and gallium nitride wide band property, then time efficiency, higher efficiency, and compact design. Basically, it's when we are designing anything, we need to have thinking about the density, power density. In small place, we can provide the higher power. So that is the density we need to take care about that in this power means power component generation. So that's what that is the main applications we are targeting for this automotive application with advanced semiconductor industry. So how the traditional advanced semiconductor mainly just difference is what is the currently available silicon. So there is also advantages currently in some low cost is there. Then it's a mature technology. See, a very when any industry is evolving for new trends or new thing, but traditional things also we need to consider because this is easily available. And challenges is here is that if you are adapting the new technology, first one is the availability of the material. Sorry, easily availability of the material, availability of the technology, then resources, man, machine, then skilled person also. Because this is the well-established industry in the silicon, and now it is shortage is coming in the silicon semiconductor industry, but this is well matured. But here we have some limitation actually. In that limitation, we cannot do the some high performance applications. That's what we require some wide band gap applications for the semiconductors. That's what we are evolving this new technology in our technology for power electronics in electrical vehicle, some autonomous driving and software defined vehicle. So basically V2G also is there, G2V also is there, vehicle to grid, grid to vehicle charging also is there, and different converters basically power electronics converters we are using this. And this is future what we are thinking, and we are proposing in new trends in the industry. So EV application, how the EV is evolving with the new semiconductor actually. So basically, when we are targeting about the electrical vehicle, we need to have, say, in IC engine, internal combustion engine. By petrol, we need to have some fuel average actually. So same things we need to efficient. We need to make electrical vehicle as efficient by using the semiconductor, because if battery we are using this, so we require we every customer is targeting the range. Means I required more range for this electrical vehicle. So how we can utilize this higher efficiency? This is a two way. First one is that utilize the semiconductor or utilize the power board as an efficient way by switching the PWM frequency or some switching applications to deliver the correct power to the wheel by the battery, and utilize proper power. Means do not waste the power, means power losses, reduce the power losses by using this one. Second one is a high performance application. So if you are going for the high performance applications, so it will increase the speed of the computation, and increase the performance of the vehicle also. So that is one thing for the driving range also increase, performance also increase, and it is nice to have. And in customer satisfaction is a more rather than the conventional silicon applications. So that is the EV applications what we are targeting with next generation semiconductors. Sorry. So next application is we are targeting as a autonomous and ADAS system actually. So now you know that in mission critical applications, some vehicles applications also is using the autonomous, means without driverless car is on the road is coming in future. Some of the countries it is already revealed on the road, but due to road conditions, some of these things it will may postponed, or it will come in the future, but after some time, but it will definitely come. But in that autonomous, we need to have some high performance computer in this vehicle, because driver is not there. So any action we need to take as an immediate basis, so there is no delay. So that's what we required, some high performing semiconductors to execute the instruction from the sensor, and taking the necessary action for the driverless car. So that is the autonomous. And ADAS applications, basically advanced driver assistance system. Even driver is there, but if something is happening on the cruise control or advanced cruise control, so vehicle or controller will take care about this, any malfunctioning or any actions with respect to, it will hazardous for pedestrian or it will hazardous for self vehicle also. So that is one applications, and autonomous and ADAS we are targeting on the next level semiconductor industry. And what are the basic advantages basically for thermal, in case of thermal? Because in EV, it's a high voltage application, then high current applications, and also it's high switching frequency applications. Okay, so in that case, we are increasing the temperature also, and in the battery also, we have some chemical reactions also to in that chemical reaction, in may chance to increase the temperature. So cooling mechanism also we required. And how is sensing part also is there. Some semiconductor MOSFET also, self heating also is there. So that is one point. And external component also heating. So taking the care of this other components, as well as taking the care of some self care, we can say that. Example, silicon MOSFET I'm using. So some of the properties there, you can hit after some times, or high switching frequency. But in this future trends, it is it's capable to sustain the high temperature also. That is operated at high temperature in the reliability and thermal properties. It is like reduce the cooling size, system size, and all. Because if the material itself taking care of this temperature, then no need of the higher side of the cooling. So that is we mentioned here. uh, Now we discuss about the high in advanced semiconductors coming in industry. We are utilizing this. See, everyone has, again I told, pros and cons. This is okay, means we are using the high performance computing semiconductors. But in that case, again some challenges is there. Current we are it's a higher material basically, and mostly some of the times we are not getting the material. So first challenge is that availability of the material immediate basis. That is the first point. Second point is that uh, some uh, some scaling of the. And again, if you are designing any system, we need to have design as a cost effective solution. So if less material means higher cost, and the complex algorithm also is there. Some cost effective cost also involved in this silicon carbide and gallium nitride actually. So that is the some challenges is there. But yeah, definitely it will in future industry going towards. So once material availability will done, some of the places it will reduce the cost. And if we are using this some of the critical applications, we can target for this cost effective solution with these new trends. Then future trends increased about silicon adoption of the silicon carbide and gallium nitride. Actually, it's evolving in EV industries, and I told like in autonomous car and ADAS features also. So integration with wide bandgap power modules. In I told like power modules which we are using as the converters, power converters we are using in this power modules. And basically it's fast charging and V2G technology, vehicle to grid technology, and charging also. So now see current vehicle, we can in the petrol vehicle we can we can fill the petrol immediately and we can start the vehicle. But in charging vehicle, actually current also we require some of the times to charge the vehicle. So in future we need to charge the battery as soon as possible within the less time. So by targeting this, if we are using this power electronics, we can able to sustain the current and voltage. So if current we are sustaining and voltage we are sustaining, we can provide a more power in the power by the power electronics, and we can charge the battery. But again, we need to take care about the trade-off between the battery capacity and the charger capacity. So that the power electronics we can use in this charging mechanism. So conclusion, basically, what we are concluding here is its future trend mostly we are evolving in the high performance computing. That is one thing. Reliability, then time constraint and mission critical application, and EV industry. Some EV industry is moving towards the some means it's we require some less time execution actually. So that is the point we are shifting towards the silicon means for future trend semiconductor applications. And again, in EV, actually, EV mostly required the power electronics. Actually, it's total gaming on power electronics. So that is the main confirmation of this EV industry evaluations. So that is a conclusion main we are targeting actually. So yeah, that's from my side. Brief about this semiconductor industry and advanced semiconductor materials. Yes, we are open to about the questions. Yeah, yeah. Thank you. Yes, ma'am. Yeah.
Yeah, yeah. Any questions from the audience side? Within 25 minutes. Ravinder, you are expected to speak for 1.5 hours.
Oh, yeah, yeah. No, no, actually, we have means we discuss about discussion and presentation actually. So you can,
Okay,
if
so
question is
one-to-one
there,
interaction you wanted.
yes, yes, yes. Means actually, this is a new technology, new innovations and all. So
Huh.
yeah, here also some diverse size members also skilled member, diverse size member also is there. So with this, any of the points we can discuss. See, we have many points here for the some challenges, some innovations. So we can discuss anything on this future trends.
Yeah, but then by the time the questions are there,
Yeah.
can you elaborate on some of the things which you feel can be understood by the diverse public, faculty members?
Yes, yes, sir. So actually, in with respect to VLSI, currently we learn about the VLSI design also and all. So basically, we are targeting some leakage application on the silicon base actually. So now future trend, how the future trend is evolving. So with respect to how the semiconductor is evolving, that is most related work to the what customer is demanding and what the future trend is going and why how we need to give our knowledge to the our student. Okay, so that we need to adapt the future semiconductor to the in education also in practicals or some uh, I mean some knowledge sharings also, so that our students also will encourage towards this the future trends with this semiconductors and all, means everything actually.
Mm-hmm.
Yes, ma'am. And again I would like to have some means the student also need to have some connectivity like in industry what is going on, because we are doing study on this books and all. Apart from this also, with this parallel base of the books, we need to have some discussion or some keep in mind as future trends what is going with this related study actually. So that things
Mm-hmm.
also we need to adapt. That is I would like to convey. Yes, ma'am.
Yeah, who's the next speaker? I have to see, but I don't think she will be ready within like 1 hour previous. Uh, what else you can engage the audience with other expertise, with other knowledge sharing, which you have expertise in? Can
Yes,
you
yes.
elaborate some of the slides?
Yeah, 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 yeah.
Till I see the next speaker is ready by that time, meanwhile.
Sure, sure, sure. Okay. Okay. So, what we will discuss about this industry, sorry, semiconductor in terms of the EV application. So now, let's say for the EV applications, basically how it actually is using this advanced as applications. So consider we have the EV, and now we need to have some converting the battery energy to the motor. How it is happening basically in this using the semiconductors. So previously in IC engine, basically once we are driving the drive by the car via the accelerator pedal. So it's converting in the control. Basically, previous one control is a regular control, which can taking the signal and converting the in this signal as a throttle valve control, and then it is delivering the energy to the by the engine to the wheel. But here, when we are pressing the accelerator, we need to have some conversion. First one is a normal semiconductor, which we can send a vehicle control unit. It will give some commands to the power electrons, our power electrons. So we have different section of the power electrons, basically for one minute, EV application. So in that, one minute, yeah. So here, this command, basically this command, vehicle control unit, command going to the our inverters as a power electronics board, and then onboard charger and DC to DC converters actually. So how it is happening basically? So one command example, I want to drive the car, basically, and this command is going to the vehicle control unit. So vehicle control unit has one some semiconductor logic also, and software logic also. So in that, it will go command to the power electronics. So as an inverter to drive the wheel basically. So in that power electronics, one command is converting the torque, and we need to have some DC conversion to AC conversion. So in that, we have three legs controller, and in that three legs controller, basically the power electron MOSFET or IGBT, any of the applications we can use as per this our demand, basically high current and high voltage. So this power electrons, basically it's working on the PWM pulses. Basically, we learn these things in books also. But why I'm taking as opportunity is that we are discussing about a practical application. So once the pedal command is came, then VCU to the inverter motors. Inverter motor will convert this PWM pulses. What are the power I required to the motor in via the this MOSFET as a three leg control. Basically, upper leg for this. Three MOSFET, up layer, lower MOSFET, lower level also three MOSFET. So main aim is the DC to AC. So in that, one thing is using this advanced semiconductor is that timing base actually. So I can draw, but yeah. So actually, in time base means if upper leg is disconnecting or lower leg is connecting, means the lower MOSFET is connecting, is a high pulsating pulses is provided to the MOSFET. So this is the capability of the semiconductor to adapt these pulses, because after that also, if you are increasing the frequency in current semiconductor material, it will generate the EMI and EMC, electromagnetic interference and all. So it will affect on the our performance. That's what, if we are using this semiconductor and conductor as advanced, so we can reduce our EMI interfaces also. We can reduce our means we can increase our computation computation speed also. So performance we can increase. Again, if we are transferring our power from one form to another form, like a DC to AC for a motor, so we are providing the switching command, but it exiting on fast with this advanced material. So efficiency also increase in this inverters model. So that is the application is then the motor control application. Onboard also is same for charging the battery actually, and a DC to converter for the charging of the small battery actually. So this is using for the high voltage battery charging, and this DC to DC converter using for the high voltage to low volt battery, because we required high voltage like 320 volt battery, and for DC to DC converter using for low voltage 12 volt battery, from this high voltage to low voltage charging. So that three application basically we are targeting, or in future also, it's a trend is going to utilize this semiconductor material. And mainly how why we are using, because high efficiency, then design also we need to compact, because if you are doing the design good, then it will increase the range of the vehicle also, and the complexity also will reduce. So that is the compact design. And high reliability, its material is good, then it's a long run. If I'm using this material for this advanced material, so it's a high reliability, means in the long run applications we can utilize this material. So that's the application basically what we are using currently. Yes, ma'am. Yeah. So any questions related to this? Anyone have?
Participants are requested to raise the questions, or you can put the questions in chat box also.
Okay, yeah. I'll see the chat box also.
So now, what are the recent developments in EV related to semiconductor?
Okay, sir. So, yeah, I told like in recent in EV industry, basically more focus area charging time. Okay, and second one is efficiency. So I told like in petrol vehicle or diesel vehicle, we can fill the petrol or diesel and we can go immediately. But in charging case, we need to stop the vehicle, we need to charge the vehicle, and we need to go. So in that case, now fast charge are also coming. So if fast timing we need to reduce for the charging, now it is coming focusing on this fast charging. So if I'm targeting on the fast charger, I need to have some capability for thermal management also, then fast competing semiconductor also in power electronics actually. So this semiconductor is using this semiconductor, we are making the some power board power electronics to have some fast charging capability. So that is the applications it's focusing currently actually. And efficiency is reverse, like I charge the battery, but I want to utilize this energy to every component, like some DC to DC converter is there, some my vehicle equipments also is there, some inverter also is there. So I need to have some efficiency, efficient converters means transferring this battery power to every equipments. So that's also I required the semiconductors to increase the efficiency. So this is the two targets mainly in future trends actually. Yes, sir. I hope I got given what you are expected answer.
Now, what are the these different opportunities for students in these sections, and what are different job roles for
Yes, sir. Yes. Okay. So in terms of job roles, see, two approaches there. One is hardware related, and one is software related. See, in future trend, high performance computing machines or some controller is coming. So in that we can have means students should be aware about what is happening in the industry in terms of the HPC, high performance computing, and second thing is that how it is controlling on the past and how capable this hardware or this semiconductor chips to handle this which application actually. So application based students should be know about the actual hardware as a chip. Second thing should be know about this control mechanism or controlling speed, and third one is the application basically where we can adopt this utilize of this advanced semiconductor to critical applications actually. So that they should aware about this all the things actually. And if we go depth level again in microelectronics, they should know about the how the chip is making as a high performance competition or in advanced semiconductors. So that they should know also.
now, conventionally, we are using silicon material,
Yes,
basically.
yes,
Okay.
sir.
So, what is the current trends in the EV? That is, whether they are using any advanced semiconductor material.
Yes, sir. Actually, now also some of the applications using the silicon. Not some of them, means every application. But in future, because see,
Which,
every
which which materials are used right now? So,
silicon.
only silicon. Okay.
Yes, yes. Because first one is the availability of the silicon carbide.
Right.
Second one is the cost-effective solution. Because in EV industry, if someone is doing the development, it should be reliable or valued cost to the customers also. Okay, so that is the silicons are using currently, but some of the applications, the advanced semiconductor using like high performance computing
Okay.
or some higher side power electronics.
So now, in terms of semiconductor, what are different roles that can be played in this modern vehicle by semiconductors?
Sorry, sir. Sorry, 1 minute.
Means semiconductors is everywhere right now.
Yes, yes.
What are the recent that is the roles that are played by semiconductor right now in EV vehicles?
Yeah, yeah. So here semiconductor one is a control board basically, which we are using the like DSP and DSP and microcontroller actually. Digital signal processor. One is a control side, and second one is a power board side. So in that power board side, we required some driver board actually. Driver and in the sense handling of the voltage and current. So basically for high voltage, we need to transfer to this pulse by using the control signal like SMP switch mode power supply. By using this,
Hello, Ravindra, you are mute. Just unmute yourself. Hello, unmute yourself. Hello.
so automatically it is going off.
No, no.
Mute. Okay,
Yeah, yeah,
now
yeah.
No, no. From my side, I have just unmuted all the participants to raise the question, basically.
okay, okay, sure, sure.
Burkai sir, was this question asked? How the energy management part is handled in EVs using power electronics?
No, 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 ma'am, no, ma'am. I have asked my own
Okay.
questions, basically.
Okay. We have one question in the chat.
Mhm,
Vrushali is asking how the
mhm.
energy management part is handled in EVs using power electronics.
How energy management? Sorry, madam, can you repeat?
How, yes. How the
Mhm,
energy management part,
mhm,
okay, is
mhm.
handled in
Yes.
EVs using power electronics.
Yes, yes. So we normally in energy management we require BMS battery management system. Energy is a part of the battery, basically high voltage system to storing the battery charge in the high voltage battery. So in that we require battery management system. So in that also for the battery management system we have computing machines or controller signal processor, digital signal processor, which we need to taking the signals from every cells basically in battery. If we are considering about the battery design, we have the number of cells connected in series and parallel, and also temperature sensor also is there, voltage sensor also is there. Then we have some contactor latching contactor also is there, and some current sensor also is there. So by taking this all the data in the computing machine as a battery management system, so there also semiconductor is using actually is a performing the high computing to taking the data and maintaining the health of the battery and protecting health of the battery also for self protection and protection about the environment also. Environment in the sense vehicle. Example, I'm using this battery on the vehicle, so it should not affect your battery on this external environment in the battery vehicle cabin and all, and it should not affect on the battery casing or any other adjacent cell also. So there, it's taking the all the signals and performing the high computations, and then maintaining the like thermal runaway case is there. We need to detect thermal runaway case also is there. And other protection like overcurrent, voltage and all. So we are using this chips there in the BMS battery management system to avoid these scenarios in the effective energy management system. Yes,
I hope, Vrushali, you got the answer.
There is one more
We have one
question.
more question.
yes,
Okay,
yes.
continue.
Yeah, specifications of inverter used
Mhm.
for traction motor.
Mhm.
Can you give the specifications of the inverter used
Yes,
for traction motor?
yes. See,
Dr. Dhule wants the answer for this.
okay, okay, sir. So basically, specification point of view. Example, first we are defining the what are our range in the vehicle, actually electrical vehicle. So as per this vehicle range, what are the capacity of this motor? So what capacity motor I required? Example, I'm giving the example. It's not the correct data, but in example, let's say my motor is a 50 kilowatt motor I want to use, and I need to create some 45 Newton torque for this motor to run my vehicle. Okay. So with this specification of the motor, I need to define my power electronic board to deliver this power. Means current, I need to give example. I need to provide the 40 ampere current. I need to provide some maximum voltage, 100 voltage. So this is a specification: voltage, current, and with motor temperature performance also, means power board performance also. So with that, I need to select. See, my voltage range is fixed, my current range is fixed. So accordingly, I need to select the power electronics devices. Example, I need to select the MOSFET. So with this MOSFET, actually, how we can select what are the MOSFET capacity? First one is a voltage range of this MOSFET. So my application is like example 320 volt can sustain this MOSFET, and 400 ampere current can sustain the MOSFET. But it is not like that. I need to give some buffer. So I will select around 20, if I'm considering 20-30% above. So this semiconductor can handle the over voltage also. Example, 550 voltage also can sustain, and again current also 450 current also is sustained. So this specification, motor specification, then we are doing this controller specification, and then final specification going on to power board generations.
Dr. Gule, you can unmute yourself and you can ask the question to get more clarity if you want.
Yes, please.
Hello.
Yes, sir. Yes.
So traction means basically when we are starting at the moment, there must be some surge current, high
Yes.
current, which I need
Yes.
to consider.
Yes.
So that's I wanted to know whether it should be 1.2 times, 1.5 times, twice.
No. See, we have this two specifications actually. One is a continuous and one is a peak. Okay.
Yeah.
So in that case, basically peak we are considering as a maximum current, how much we can provide. Okay, that is one
Yes.
thing. So current and voltage, it's a trade-off again. See, example, my controller, my controller able to give the continuous current 200 ampere, and my peak current is at 300 ampere. Okay, so at that time, what is my specifics? I can make my reliable controller. My peak, my totally controller is based on the peak current actually. It's not the continuous current. See, if peak current I design, then almost it will happen on this normal control actually. So I will design my controller above the peak current actually, and peak voltage. So I will design, like example, my peak current is 300. So I will design the marginal design as a 350 ampere can sustain. And after that, if even though this is happening on the overcurrent, means peak, and again this is again consideration, peak current is on time based. So how much time I can sustain this is my controller, means semiconductor, like 1 second or 500 milliseconds and all. But above 100 is going, then is going for the derating, means voltage, even though current is increasing, I cannot increase my voltage. So I'm deliberately derating my controller and going, means derating my voltage. So curve will be equal, like power voltage into current as a power, equilibrium of the power. I hope this is okay.
Yeah, okay.
Sir?
But designing with the heat sink, then whether they are considering the peak current or this continuous current.
Peak current actually.
Designing of heat sink. Yeah.
Peak current, sir. Because why peak current? Because if you are considering the continuous current is execution of the our controller, but peak current is a time base. Above on this time base, it will go off actually. It's a time base. If example I told, some peak current 300 for 500 milliseconds, like that. So that we design for this controller for the peak current basically.
Yeah. Okay. Yeah. Thank you, sir.
Okay, sir. Thank you. I hope you got the clarity. Even if
Yeah.
any
Yeah.
details is
Thanks.
there, let me know. We'll give details.
You have one more question from
Okay.
Mrs. Deepali. She is asking, what is the difference of EV and hybrid electrical vehicle?
Okay. Okay. So in terms of EV normally in electrical vehicle, proper one battery we are using. It's totally based on, means energy is based on the battery only. There is no other supply or any other supply source of this power in the battery is called as electrical vehicle. And in hybrid, actually, it's not exactly hybrid, not exactly IC engine, means engine, or not exactly the battery. So they have one battery also is there, one engine also is there. So this is called as hybrid actually. So in hybrid also we have different topology, like small battery, big engine, we can say the hybrid, or big battery, we can say small engine, we can say the hybrid. Again, we are small battery, we are using some of the motors, example P3 motor, P1 motor, P0 motor. You can just note it down for the motor position. P means position, and with this position, example, my motor is placing on the gearbox, it will jerk the power. It will not completely EV, but it will help to increase the performance of the vehicle by using the battery, but it will support to the engine. So that's called a hybrid actually. So that is a difference, basic difference. I hope, ma'am, you got the answer. Any clarification required?
Yes, so it was okay.
Okay.
Any more questions?
Yes, ma'am. I have one more question. That is, while selecting a different semiconductor material for
Mhm.
automotive environments,
Mhm.
okay. So, what are different key requirements? Means rather than other application, it's okay. But for
Voice is
specifically for
little
automotive,
low, sir. Can you loud 1 minute? Maybe for me. Little
what are
loud, sir.
different requirements of your semiconductor while selecting for your automotive environment?
Okay, okay, sir.
Like
So first require,
you have selected silicons or other materials you are selecting. So
yeah.
whether there are some special requirements from EV.
Okay, so basically, sir, major requirement is that some standards actually in automotive standard. Like standard is different. Like aerospace industry is different, automotive industry is different. We using the same semiconductor actually. But in automotive case, we need to this semiconductor material. First requirement is should sustain the temperature of the higher temperature and low temperature. See, higher temperature we can say, sorry, in our Indian case we can consider in Rajasthan or some of the places is a very high temperature. So our components or our vehicles should be sustained in that area also. So this is the high temperature range. If this vehicle is going on some Leh Ladakh or some high altitude areas, sorry, so these areas, so some of the minus, very minor degree temperature also there. Though these semiconductors should be work on this cold condition also and hot condition also. This is one requirement. Second requirement is the high voltage capability and low voltage capability. So on low voltage capacity, it will auto reset the controller, or in high voltage case, they should sustain. Example, if we are using power electronics, so this semiconductor should follow or allow to control the high voltage also and low voltage also. And third one is the current control. Current control for maximum current can handle with this semiconductor. So that is the basic specification we need to consider as a standard. And some of the other standard is that EMI EMC. See, if I'm using the semiconductor, it should not affect on self control also, or it will not affect on the adjacent control also, because this is a high frequency switching devices. So it should not affect this frequency on the other devices. Yes, sir. So that is the points we need to take care about this while finalizing this semiconductors.
I hope he's answered your question, sir.
Okay, okay. Thank you.
Any more questions, please, from the audience?
Yeah, please free to ask the question, many of the questions, so that we come up with this some innovative idea or innovative discussions. And see some of the things in hidden, so we can elaborate the things in on the table like that. So please ask many questions. I would like to give the answers, or I will, if I know, I will definitely I will give the answer. If I don't know, I will revert back, or I will study and give the answer.
I have one I have one come across one issue, that is high temperatures. So how high temperatures are handled by EV in semiconductors?
Yes, yes.
Because even batteries get burned.
Uh-huh.
Okay, so how these are handled?
No, sir. This is the 2 points basically. First point is that self-control. If I am giving the example, if I am the not real example. If I'm working on the security job, so first thing I need to I'm taking care of the one bungalow actually, and I'm a security. But in the first thing I need to take care about myself. If I am safe, then I will take care about the bungalow. So that is the two thing actually. In silicon also, they have some property to self protection actually. Means even temperature is increasing, self protection is sustain this at this temperature. And second thing, if again other temperature is increasing, we need to do some cooling mechanism like thermal management system. So up to some level they can sustain, but after that we require some thermal management system like cooling mechanism, some chillers and all, or some routing of this coolant liquids and all we require actually on the board also, silicon boards also, or semiconductor boards also.
Okay,
So
so
that is, yeah, yes
yeah,
ma'am.
thank you for all the answers, which were really very experience based. Our next speaker is joined. So, and the participants, if they have many more questions, we'll be sharing your contact number and mail ID so that they can approach you and get their doubts cleared.
Yes ma'am.
Okay. So the times come here to pay vote of thanks to you. So we extend our sincere gratitude, Mr. Ravindra Shinde, our esteemed guest of honor for today's ATAL Faculty Development Program. With overall 11 years of rich experience, which was seen from the answers which you are giving in power electronics and electric powertrain control systems, your session on advanced semiconductor materials and automotive applications really offered valuable industry-driven insights. Your expertise across the XEV powertrain architecture, then BMS, e-drive systems, OBS, OBC, DC-DC converters, VCU, motors, and functional safeties richly enrich the technical understanding of the participants. So we deeply appreciate your contribution through your patented innovations and your strong grounding in AUTOSAR, then embedded systems and agile methodologies. So, on behalf of the organizing committee, I once again thank Mr. Ravindra for sharing his knowledge, industry perspective, and vision for a future e-mobility solutions, making this ATAL FDP session truly impactful. So, thank you once again for accepting the invitation, sir. And the situation in which you are giving is really commendable. Like, still, you found the time and you have given us the time to share your expertise. So, thank you once again, sir. It was really great to have you in this FDP.
Yes ma'am. Yes. Thank you so much. Thank you.
I feel without taking a break, we have the next speaker here joined. So I'll introduce today's speaker to us, and then we will start with the session. After which, then, if you feel, we can take some break of 2-3 minutes. So, Professor Alisha, a warm and hearty welcome. To start with, I'll introduce Dr. Alisha. Uh, she is having 25 years of experience in verification from strategy definition to closure of functional verification. She has expertise in verification strategy, test bench architecture, variation plans, then experience in HDL, VLSIs, VHDL, Verilog, system Verilog, then verification methodologies like VMM, UVM, then hands-on experience on AMBA, AHB, then X13, X14, and ACE. She has also hands-on SONET, HDH, then USB to PCI Express, and experience in SOC, verification with C, and VIP-based test bench automation with PERL or Shell. Scripts for multi-core SOCs. She has hands-on on formal verifications with PSL, SVA, and exposure to low power verifications. She's worked with teams across different geographical locations with India, USA, Germany, and Israel. With the work experience with many of the companies like Nital, Wipro, KPIT, LSI, AMD, then ESCOM, and Sintra Tech Solutions Private Limited, I would like to welcome today's guest of honor to share her views and expertise with us. Madam, it is really very great to have you on this stage. So, without taking much of your time, I would like to invite you for the session. So the stage is yours.
Hey, thank you, Nita ma'am, for for the kind introduction about me. Good afternoon, everybody. I hope you are able to hear me.
Yes, ma'am, all good.
Yeah, okay.
You
So
can share the screen so that I can give you a confirmation.
yeah, I'll just share. Just a minute, I'm just sharing.
Yeah. No issues.
So everybody is able to view this?
Yes. You can go full screen and you can start.
Yeah. I had shared it. Are you able to see the presentation?
Not yet now.
Not yet.
Yeah, we are able to see your name. Just now, it was okay.
Just a minute. I'll send it again.
Yeah.
Yes. Just a minute. Sorry for this delay.
No. It's okay. You can reshare
I'm
it back.
trying to share.
Close and share it again.
Yeah. Just give me a moment.
Can I share it from my side if you don't mind?
No, I'm sharing it. Just a minute. Now I think I will be able to share. I'm sharing now. Can you see it? Okay.
But when you make it full screen, I don't know what happens.
Now is it visible?
Yeah, sure. Yes,
Okay.
it's all good.
Okay, fine. So
You can
let's
start.
So we'll start. We'll take a break of 5 minutes in between. So I'll start first. Then we will have one beginning session, like 15-20 minutes. Then we will take a break so that you can have something for doing the exercise also. So I'll start now. So good afternoon, everybody. I'm Ashlesha Gokhale, currently working as Professor of Practice in COEP and have more than 25 years of experience in industry, VLSI industry. And my main job was the pre-silicon verification. So now I start with the title, that is pre-silicon precision. So why the precision? What do you mean by precision? So precision means not just correctness, but accuracy is expected. Precisely what is required has to happen. That is precision. A single mistake is also not available, is also not possible. Not 1% deviation from what is expected is allowed. So that is precision. And we have to achieve it in pre-silicon. That's why I gave the title like pre-silicon precision. And how that is achieved, that is by pre-silicon verification. So I guess by now, actually, you would have attended many of the sessions on VLSI design, semiconductor manufacturing, and up to testing also. So you have pretty much idea about what the verification process is. And earlier you had a session for testing also, right? Suppose you have done all your efforts, you designed some application and you made all the processes up to tip out, gave it to the fab for fabrication, and after fabrication, when you are in the testing phase, you figure out that nothing is working, or some part of the your design is working, but something is not working. So that is a very bad situation, and nobody wants to be in that. No, but then what to do? Do you have any solution when you see that chip is not working? Really, you cannot do on with that chip or with that samples. The whole batch of samples which you have received from the fab, you will have to just throw away because you cannot correct anything with the fabricated chip. That's why it's very important to do the verification before the chip is stepped out, or before the design goes to the silicon. That's why we call it as pre-silicon verification. So what is verification? So verification is a process that proves conformance of a deliverable to a predefined set of expectations. So this verification verification definition applies to anything in our normal transactions also. If you go to the market and buy some product, you want whatever with the expectations you have bought that product, it should conform to your expectations. So whatever is delivered to you should satisfy the expectations. And you, before you even buy that particular good, you will check that all your expectations are met. For example, you have gone to purchase a mobile, you will see that all the features required are there. Like your camera is working fine, you are able to send and receive the messages. You put your SIM card in the slot and it's working fine. Then also within a second or within you blink your eye, when you tap the application, it opens. That kind of timing you want, right? So all these things you make sure that are working, are correct, and only then you will like to buy the product. So what you're doing in all this process is verification. You are just making sure that whatever deliverables are there are met. So that is what is called as conformance of a deliverable to a predefined set of expectations. So that is a generic definition of verification. So now in terms of pre-silicon verification, what could be the different types of expectation, or even in general? So one thing, as we see in the example, it's a functional expectations. Like all the features which are promised by the vendor are fulfilled. So all the functionality, like what kind of camera you want, what kind of speaker it should have, or what kind of memory, how much memory it has. All these are the functional expectations, right? Apart from functional expectations, nowadays there are few more expectations, like timing expectations. So the performance of the mobile also you want to be very high, right? Like as I spoke before, within a blink of an eye, you expect like the application should pop up. If you tap a particular icon and the application is taking long time, even if it's 1 or 2 seconds, you become restless and you say that, oh, this is not what I expected. It's a new mobile and the application should open just when I tap on the icon. So this is what is the timing expectations. And the third one is the power expectations. So again, with the example of mobile, you want the battery to last as much time as possible, for days, if not weeks, but at least 1 or 2 days. And its performance should be high, and then you are allowing power consumption when you are doing something with the mobile. So that is a power expectations. So these are the mainly 3 types of expectations from any design you have: functional expectations, timing expectations, and power expectations. So expectations. And nowadays I have not added here, but just few seconds before or few minutes before, we discussed that in our previous session of automotive. So that is one more feature which is very highly required nowadays. That is security expectations also. So there are some like your mobile should have some theft protection. Nobody should be able to hack the mobile and things like that, because a lot of things we are doing now with mobiles, like accessing our bank accounts and share trading and many other things. And you want your mobile should not be hacked by anybody. So we expect like high security features also present in the mobile. So these are general things which you expect nowadays with any electronic circuits, apart from the mobile also. Okay, and now as we said, like all these expectations has to be met, and that has to be ensured by verification. So as we have already seen, what are the phases in which actually the development happens? First, you define the specifications, then you do the design of the specification, and then you go for implementation. So when you start with any design, any new design, say you want to start an IoT application. So you have in mind, first of all, what kind of system I want to have for an IoT. Say it's an agriculture application, then you will think what should be the range by which my application should work, what is the distance I need to cover, what should be the, like, if low power, obviously the leaf nodes should have the low power expectation. So all these things you are going to document. What kind of functionality you want, what kind of timing performance is required, what kind of low power modes are required. All these are the specifications. With those specifications, you will go for choosing the design, or actually fitting up design for that. See what kind of SoC I require, what should be the main processor, what should be the protocol for connecting to the leaf nodes, what the leaf node should have, like what kind of sensor it needs, what type of protocol I want to use for transferring data from leaf node to the main node. All these things you will consider in the design. And once you have all these things figured out, how you want to implement a specific application, then you are going to go for the design, for the implementation. So part by part, you will start bringing the components and then assembling together, making sure that they are talking to each other in a really nice manner. There is no miscommunication between these components. And finally, you will see that everything is stitched together correctly and your specifications are made. So these are the development phases for any of the projects. Same is applied for the any VLSI design also. So now we will see some interesting Venn diagrams over here. So we have the design intent circle, specification intent circle, and implementation circle. So here, if you see in the diagram, B, E, D, F, all these consist of a specification. So suppose you have a yellow circle, which is a set of specifications you have done. And design intent circle is that red circle, which is also formed by A, E, D, and G. Okay, so if you can see the cursor. So A, E, D, and G. So this red circle is basically the design intent circle. So the yellow circle is a specification, red circle is the design intent circle, and green circle is the implementation. So what has happened? So this is what you want to do. This is what you have actually designed to do, and this is what you have. So you will see some overlaps and some gaps. So if you see the part E, so what is E? This is a overlap between specification and design intent. So whatever was specified, what you intend to have, the part of that has been covered. That is good, that E. So it is a overlapping part between specifications and the design. But vast of the part A, that lie outside the specification circle. This means what? Whatever you had wanted to have, apart from that, you have added something which you actually don't necessarily want it to be there. And similarly, so there is some disconnect between the specifications and the design. And now finally, the C circle is the green circle. Okay, so green circle is the implementation circle. And you see portion which is C, which has come there, which was neither you expected nor you designed to have, but it is there. So that is the implementation. Obviously, some part is there, whatever is in specification, and it's also there in the implementation, that is F part. And there is something actually the specification didn't specify, but the design had, and also therefore it is gone into the implementation. And then you have a small portion over here B, which is what is specified, what is design intended, or what you design for that particular specification, and that's got implemented. So there is considerable disconnect. So we will see each one why it happened. So A specifies a wrong capture. So you capture something which was not even intended, but because of your own misunderstanding or your what you say, bias thinking about the design, you have something which is not captured present in the design, but somehow it didn't even get implemented in the final implementation. So you have this part A, which is wrong captured and not implemented. As long as it is not implemented, good, but you have wasted a lot of efforts to design this and actually making sure that you gather the components for this A and things like that. Then part B is something which is very bad. Something was expected and it didn't go into design, and that's why it is not even in the implementation. So half of the specification you have missed out if this is the case. Then part C is something which was not captured, not designed, and still implemented. Now, why this will occur? Say you are working earlier with some design and you take it forward. Some you think like, okay, this design can be modified a little bit, and then I can make this as some other design, mold this into some other design. So lot of legacy things are there. You make this, you do the modifications to make this work, but then there is a lot of things which are not even expected, but they are lying around there. And so you have this area C. So the implementation will have something which is not defined by specification and it was not even designed for. Now, what's the problem if you have something extra? It may lead to some wrong functionality. So we will see that later on in the example. So there should not be something which is not expected. Okay, so these are the different things actually, like where something can go wrong. And we have to focus on this area D where everything is coincident. So the verification is a process for demonstrating the intent of design is preserved in all its circles. So whatever is your specification, that is coinciding with the design, and the same thing coincides with the implementation. So ideally, all these three circles should coincide. And there should not be any areas left out like A, B, C, E, F, G, only D should remain. So that is the process of verification. I hope this is clear. So we'll move to the next scene. So we'll see now, this is a general process applicable to any design, not necessarily pre-silicon. So we'll go see to what is pre-silicon fabrication. So before the chip goes to fabrication, that is in silicon, we need to ensure the design is work-free. So earlier slide has shown all the different things, different circles, and they are not coinciding. So because of that, there could be a lot of bugs. Whatever you expected is not happening, or what is not expected to happen is happening. So all these are the bugs. And in pre-silicon verification, we have to ensure that there is no bug left when you are giving the design for the fabrication, that is to get into the silicon. So the design could be whatever complicated. We must ensure that it's all verified and there is no bug left. It is error free, absolutely. Because as in the beginning of my talk, I said, say you give your design to the fabrication, and if you get out that design fabricated, you have the chip now, but it's not working. You just cannot do anything to repair it. There is no repair possible. So this is achieved through simulations. And what it basically means is you have to create all the possible scenarios to occur in the lifetime of the design, ensuring it works correctly before it gets actually realized, right? And that is how you do that, by using the simulations. So before something exists, you have to make sure that that something is already correct and there are no bugs in it, and there should not be any bug in its lifetime also. And so you have to simulate everything beforehand. So that is a pre-silicon verification. Obviously, this is a very tedious job. So as the designs become more and more complicated, the efforts for verifying the complicated design also are exponentially high. So almost 80% of the efforts are put into verification in any design and development cycle of a semiconductor chip. So if you have, say, 10 engineers team, then you may find only 2 engineers are really working in the design development, and 8 engineers you will see working on the verification part. Because now we'll see in the proceeding slides where all these high efforts are required. As I've talked before, repair is not possible when design is fabricated. Okay, so that's the thing which makes so high efforts you have to put into the pre-silicon verification. So it's okay to put high efforts and spend more time before the design goes to fabrication, because if you fabricate a wrong chip, then it obviously calls for the respin. So what is respin? Again, doing the same process of simulating everything, simulating the design, synthesis, circuit simulation, creating GDS2, then getting the time from the fab for your chip to get samples for. So all this, the whole process has to get repeated. Also, there is a huge value associated for getting the chip fabricated. So the value, the money goes for respin is very high, in millions of dollars. And obviously, when you are not come up with the right chip in right time, there is a delay to the market, and that is creating the potential loss of business. If a bug escapes the testing and appears after the delivery to the end user, it's again a huge loss, monetary as well as a reputation. So what if that wrong chip is the bug got escaped even from your testing part? Okay, so some product has been built. Say you have built your own phone, mobile phone, and there is a bug, like suppose you click something, some other window is getting open, and this thing is not even got caught in your testing process or during the application development cycle, and something happens, and the kind of arrangements are there in the user application. Say user downloads multiple application, and then he finds, like, if I click on something, some other thing is happening. So if user finds it, what will happen? It's a use, like you will have to refund to all those users to which you have sold your device. You have sold your, say, mobile. And so that's a huge loss. Plus, the reputation of your company is also gone, because people will talk about that. That will be on your social media, like the product of such XYZ company is buggy, it is not performing. I have got this bad experience. I've got that bad experience, and obviously the reputation is also lost. So in many cases, if there is a startup or something, they will have to shut down and they will be bankrupt. So that is the cost of a bug. If the bug escapes all your verification process and testing, it's a huge loss. And the classic example of Pentium floating point bug was $485 million, and that is some 20 years back, 25 years back. So that was a huge loss to Intel, but it was Intel, so it was able to recover from that. Otherwise, any small company or medium-sized company would have gone bankrupt. So I hope you understand now why pre-silicon verification is so much important. So let's move to the next slide. We already talked about this. So basically, we will see how the verification process works, at what stages you have to do the verification, and how the cost of work increases with verification process. So if you look at the graph here, if you see at unit level, it's very low, less cost, like negligible or close to zero. So that is a process where you are supposed to find all the bugs, that is unit level verification. It escapes the bug escapes unit level verification and goes to subsystem level verification. Then still it is fine. Actually, you are in the design and development phase still. So you can find out the bug, even though it is now a little bit difficult to find the bug at the subsystem level, because 3-4 more modules you would have integrated, and figuring out where the bug is exactly will be a little bit difficult, but at least you caught it in time. So still the cost of bug will be less. Then say after the system level, it goes to the from subsystem level, it goes to the system level verification. Now there will be a whole lot of people involved at this point. Earlier, up to unit level and subsystem level verification, the small teams will be there. There will be good communication between each other, and it would have been very easy to figure out the bug. Now the bug goes into the system level. So here is shown over here, like what I mean by unit level and subsystem level and system level. Say memory, CPU, and peripherals. These are your units. And memory and CPU, if you're connected together, then that becomes a subsystem. So earlier, if at unit level at the memory verification itself you catch a bug, or CPU verification itself you catch a bug, it's very easy to fix it. You do have to do the testing only at the CPU level or only at the memory level. When you have to the system level, subsystem level, you have to connect two things together, memory plus CPU. So now it becomes a little difficult to figure out where the problem is, whether the problem is in memory or in the CPU. Say you are doing some read and write, and CPU reads some wrong data. CPU gets the wrong data after executing, say load from memory. So now where the problem is? Is this problem with CPU module or with the memory module? That's a question. So both the modules you will have to verify again, figure out where exactly the problem is, and then again integration testing you will have to do, like again connecting these two modules and check that no other bug is there. Plus the bug fix, you have to make sure that the fix is not causing any other damage also. So at unit level it was very easy, at subsystem level little complex. Now imagine like multiple modules are connected together. So memory, CPU, and multiple other peripherals such as your say USB module or Bluetooth module and whatnot, SPI and other things are connected together. And now you find a bug. How you find a bug? Basically, some test case will start failing. Now, when the test case starts failing, you directly don't know that exactly it is the problem between the communication between CPU and memory, or in the interface, or it is in the peripheral. So you will take a lot of efforts to find a bug only, what exactly the bug is. So efforts are high, but still it is within control because there is no tipped out. So it will get spread into multiple different teams who are working together. And also the cost for this, like efforts of all those people who are working on this particular system design or the system level chip, are going to get vested because of this. So a lot of investment has to be done for this verification efforts. So the cost is high, but it limits up to the efforts of the team only. Now, if you see this particular graph, this part is a validation. So you see how drastically this cost has increased. Once it goes to the fab and you tapped out, and then in the samples you find there is a bug, it's a huge cost, because now again the whole process has to be repeated. Multi-fold, the cost is increasing. Then this is the stage where you caught the bug in the application. So again, multi-fold increase in the cost of the bug, because you have to go for the respin as well as figure out who is correct, whether if the application is right or the software is correct or the hardware is correct, and lot other things are there. Also, you lose some potential market because of this delay. So again, huge cost is involved. And this is the thing, this is the graph, black one, which is showing the cost after it goes to the customer. So you will see how big it is. So it's 500 times what was, like some hypothetical situation, 500 times the unit level or infinite times as compared to unit level, even multi-thousand fold increase as compared to the subsystem level fixes or system level fixes. So it's very, very huge. So you can see that cost of the bug increases exponentially at later stages when it is found. So now we will see when to start the verification. So people usually think that verification has to start, that pre-silicon verification has to start when your RTL is complete, and then you want to do the testing part, or so you want to run the simulation. But that's a misconception. This is a verification process starts right at the architecture level. So when you have the system level specification, from the system level specification, it is decided what part goes into hardware, what part goes into the software, that is defining the partitioning. At that time itself, you have to do some functional simulation, whether this assembly is really going to work or not. So if you have, say, C models of all the hardware components, then you stitch them together and see with these models, whether conceptually your solution is workable or not, is feasible or not. So the verification process starts exactly at that time. Then that hardware is broken down into the architecture, which is suited for the design, and multiple modules, subsystems are created from the architecture. Hello, am I audible?
Yes, ma'am.
Okay.
जब आएगी तो अपने मेडिकल डॉक्यूमेंट लेके आएगी.
Hello. Ma'am, just unmute yourself. I just mute all participants. Vaslesha ma'am, just unmute yourself. Hello. Is it audible?
You are audible, but then Gokhale ma'am, you have mute yourself. Can you please unmute?
Now am I audible?
Yes. You are audible now.
Okay, so
Yes. Hello.
Till what point actually I was audible?
The last slide.
This slide which I'm presenting now.
Yeah, before that.
This one.
It didn't change. Yes.
Till this point, I'm audible, right? Okay, so
Yeah.
we have not. I'm audible?
Yeah.
Yes, ma'am.
Okay, fine. So I was explaining about the design. So the design is broken down into different modules, and for those module designs, you do the RTL coding. So the simulation starts from that point in design. When you write the SVL description, then you start your simulation either with behavioral models or you write the code in HDLs or HVLs, and you start simulating. So there the actual functional simulation happens. Then after functional simulation is complete, like you have done your RTL level verification, then actually the synthesis happens. So in the synthesis process, the whole behavioral design gets converted into the netlist. So that is a gate level representation over here. So again at gate level, you have to do again the verification with fewer test cases to make sure that whatever was working at this RTL level is still working at the gate level. After the gate level verification is done, that is netlist verification has happened, then you proceed for place and route, and finally the physical design part. So that gets converted into the actual circuit design. When you do the physical design part and optimization is complete, you will get to know actually the timing delays over here. What are the clock skews, propagation delays, transport delays, all this timing information you will obtain only after circuit design is done. And once that timing optimization is done and you have all the timing information, those are back annotated to your netlist, okay, which is a list of gates and the connections. In between, you are also insert the timing. So with this timing inserted or back annotated netlist, again you have to do the verification to make sure that the performance is met or the timing expectations are met. After that, you go for the physical synthesis and GDS2 is obtained. So you have kind of a physical verification also, but we are not going to discuss the physical verification in this. So after physical verification, you go for the GDS2 where you get to know the information about your metal layers and how much, where what are the N material, P material, transistor width, and all those things, like what is the 3D image of that particular device and things like that. So you will have this GDS2 files in this form, and then it goes to the fabrication. Then after you have the silicon wafer fabricated with all your design, it is packaged and delivered to you. And after this, you have what is called as verification. So I think by now you would have gone through this whole flow multiple times, so we'll not spend much time on that. But the main point is the verification process starts exactly at the defining of the specifications only. So we are talking much about the bug and cost of the bug. So how the bug is defined, let's see that. A bug is a defect, mistake, flaw, or error in the design that prevents the design from behaving as intended. So basically, it's deviation from the expected functionality. Something is supposed to happen and that is not happening, then that's a bug. Suppose you have designed an AND gate and you know that the AND gate result should be like, if both the bits, both the inputs are 1 and only then the output is 0, then it should work exactly like that. Suppose both the inputs are 1 and still the output is not getting 1, then that is also a flaw. And even if only one of the gates, one of the inputs is getting high or getting activated, asserted, and still you are getting output as 1, that is also a bug. So anything which is not expected as per behavior is a bug. Now, why the bug should occur in first place? It is because of the misinterpreted specifications, misunderstanding of the design, incorrect specifications, missed scenarios, and assumptions. These are the primarily cause of the bugs. So all these things we have already discussed in the first scenario where I have shown you the 3 circles, right? So the specifications itself are misinterpreted. Then that whole yellow circle, if you remember, which has the specifications, will not be captured correctly in the design. Something will be added, something will not be correctly understood. Then there could be misunderstanding of the design itself. So design is what basically the specifications and design, these first two things are in the form of documentation only. There is no code for this. Okay, so this has to be this can be removed only by going through the specifications multiple times, discussing the specifications, and then understanding of the design also well. So this is all about doing the documentation, good documentation, and understanding that documentation. So these two are the basic primarily sources which comes from documentation, wrong documentation, even incorrect specifications. These three are starting exactly from the documentation itself. Then you have missed scenarios, something actually which you didn't even think of when you are doing a design, and that scenario pops up, and then okay, you find that okay, something is completely missed out from the specifications also or from the design also. And then assumptions. Assumption is a very, very big cause of creating any bugs. Now, what happens to teams say are working together, and one team assumes that I'm giving out one output which will be high when it is active, whereas some other team is working on some other module, and that team expects that it will receive input which is active low. And when you when you connect these two different modules, you will see that the things are not working. Each module is working very correctly when verified independently, but when you connect these two together, then they are not working. So what is the basic problem here? This is the assumption. The teams have assumed that their output will be active high, and other team has assumed that their input will be active low. So unless these things are documented correctly, or something which you have preconditioned mind, say if you think about the clock, then you usually assume that the things will happen only at the passage of the clock. But some design has now sampling the things on the negate of the clock. So you will define the things are based on your assumptions, which has to be a passage, but actually that's not the reality. So always these assumptions cause bugs. I hope the point is clear. To avoid these things, now what is the process that needs to be found for verification? So first of all, you need to identify the scenarios. Okay, even before that, there is something called that feature extraction. So in any company, there will be two teams. One team will be for design and other team for the verification. Or also there will be multiple teams like for PD and DFT and all those, but design and verification are the two front-end design teams. And as soon as the design team starts writing the specifications or studying the specifications, the verification team also needs to start with study of the specifications. So from the specifications, the verification team extracts the scenario. What are the basic scenario, not scenario, features? What are the features that are expected from this specifications or the design? And then based on that features, you identify different scenarios. From when you figure out all the different scenarios which you can think about for the design, then you go for the capture of the test bench requirement. So once you capture all the information, what kind of scenarios are required, you need to have different tools in your test bench so that all these kind of scenarios can get executed or can get simulated. So for that, you start doing the design components. We will see what are the different components involved in the test bench. So all those components are to be generated based on this test bench requirements, which comes through this scenario identification. Once you figure out what are the components you need to have in your test bench, you start coding those. So HDL and HVL coding test bench components, that is our next phase. HDL is the hardware descriptive language, and HVL is hardware verification language. So system Verilog is an HVL, and Verilog is the HDL. So certain languages are evolved specifically for verification. Then connect all these different test bench components together to form the test bench or the test environment. And then next phase is you start running the simulations for all the identified scenarios. Now, once this is done, mostly you will find a bug, right? Your bug is expected. When you write the correct code for the test bench, you have a good test bench. And if you run the simulation, mostly 99% of the time, you will find a bug. And if everything goes smooth and there is no bug, then definitely it's not that everything has gone fine in one go itself. Most probably you have done some wrong assumptions or something has gone terribly wrong in your test bench. So check for the problems in the test bench. And in obvious case, when the bug is figured out or bug pops up, then you have to debug and identify exactly where the bug is. And after the bug is fixed by the designer, again you have to simulate all the related scenarios. So once the bug is fixed, it's not enough to do simulation only for that one particular scenario, but you also have to make sure that all other related features are also intact. Otherwise, what happens? The bug is fixed for one particular code, and then it 10 different bugs popped up because of this one correction. That should not happen. So you have to make sure that when one particular bug is fixed, run all other scenarios, related scenarios, to ensure that the bug is fixed correctly. And finally, you have to achieve the code coverage and coverage goals. So this is the entire verification process. Any questions till now? So we will try to understand whole these things by an example. Now the question is how to find a bug. Okay, so the bug could be deep down your design. For example, earlier we have taken the example of the system, right, which has one CPU, then memory, and few peripherals stitched together. And the scenario is like you send the data from one peripheral, and then the CPU reads that peripheral data and it stores into the memory, and then after some time the CPU fetches the data from the memory and sends to some other peripherals. So, for example, you receive the data from the sensor and you want to display it on the display. So what will be the case scenario in that case? You have to give the trigger to the sensor. Then the sensor will send the data in the required protocol to the CPU. Then CPU will in turn stores that data into the some specified or predefined memory location. Then you fetch the data from that location and send to the display module. Or in between, you have to do some modification, some conversion of the data what you received from the sensor to correctly show at the display. You do some modifications and then you put it onto the display. So for example, you have sent a data of say 001 from your peripheral, from your sensor, and onto the display it is showing 1000, like 1000. So now where is the problem? Whether really you have sent only 001 from your sensor, whether the CPU has read it correctly, whether is there any some problem in the memory, or is there any some problem in the display. So for that you need to achieve this for creating the different scenarios. Say there is some example where in this case the data stored in the memory is stored in say big Indian fashion, like MSB at the end, and the display is taking the as LSB, like least significant bit at the end. So now what will happen if you keep on reading the data from the sensor and storing it in the memory, and again you are reading back, you will not find this bug at all. Also, if you are storing something, getting something from the memory and putting it onto the display, every time you get the correct display, and this bug will not get caught. Only when actually you are receiving something from the if only when you are receiving something from the sensor and then directly you are putting it into the display, only in that case you will find the bug. So to find such kind of bug, you will have to go through the different stages. First of all, you have to create the or activate the bug by creating proper scenario. Then you have to propagate it. Say your sensor is sending wrong kind of data, and in the storing phase actually that LSB and MSB is getting swapped. So in such case, as if in case when you are not putting it onto the display, you will not able to detect it. So activating is one part, then propagating it to make sure that it appears at the output. And then finally you have some expected data from your reference model, and then you compare it with the expected data. Only then you will find that there is a bug. Okay, so that finding a bug takes three basic steps. First of all, activating the bug by generating proper stimulus. Then again, through the stimulus only or through different scenarios only, you have to make sure that bug is propagated and reaches the output. And then you should have a good comparator which will take the expected data from a good reference model, and then you compare. So the bug will be detected. If any of this process is skipped, you will not find the bug. The bug will get escaped. So how the simple test case will look like? So basically there will be a test bench, a test case controlling a test bench, and then you have a stimulus generator and a response checker. And the response checker will finally say the test case is pass or fail. So if you see here, DUT will be a small portion and your test bench is a huge portion, right? It has multiple things apart from the DUT instance. So now you will start realizing why it will take 80% of the efforts. If you see this diagram, simple diagram itself, you will see as compared to DUT, the test bench is multifold bigger, right, as compared to DUT. So even if your DUT is getting complex, your test bench is getting even more complex, and the proportion remains same. So lot of efforts are required from the verification or the test bench building the test bench. So maybe you are already aware of what is a test bench. It is an assembly of verification components and test used by the verification team to verify the DUT. The DUT is design under test. And this test bench is mostly used in simulation environment. So whenever we are saying verification, it is mostly the simulation. And the typical test bench components will be generators, drivers, checkers, monitors, and test cases. Okay, so everyone has a role to play in the test bench. Why these different modules are required, we will see soon. Now we will see what is a test case then. So test case is a code used to generate a test scenario through the test bench. Okay. So it can control basically all the verification components or test bench components, and it focuses on activating and propagating the hidden bug in the DUT. So it's a test case's responsibility to create the right scenario with the help of different test bench components. And what are the essential part of the test case? You have to configure the DUT, select the device under test for a particular configuration. Okay. So if we take a simple example of say SPI, which is our standard serial protocol, it will have again multiple configuration, like what kind of clock frequency you have to generate, uh, on what clock edge you are going to drive the MOSI, on what clock edge you are going to receive the MISO signal, and things like that. So you have to configure the DUT first by constraining different parameters of the design and the test. Then you have to also create those scenarios. You have to configure the generators and drivers to ensure that you get the right kind of scenario generated. And then finally you will have some part of checking. So you may have some scoreboard or a checker in place so that it will compare the expected value and actual received value. So some part of checking is also done in the test case. Okay. So before we proceed, we have to make sure we have to understand how the simulators basically work, because we are talking a lot about simulations. Verification is nothing but running a lot of simulations. So let us understand how the should we take some 5 minutes break here and then proceed? Hello?
Yes.
Should we take a break now and then because
You want a break? Then we can take
just 2 minutes
2
break.
minutes. Yeah, yeah.
Yeah.
2
And then
minutes
we
we
will.
can break.
Huh.
Okay. All the participants, we can have a break of 2 minutes, after which we'll resume. Keep connected. She'll be back.
Yeah. So I hope everything I speak is clear and
Yeah, yeah, yeah.
because I
It's
cannot
very
see.
interesting going on.
Okay. So should we start? Hello.
Yes.
Yeah. So we'll start again.
Yeah, yeah. You
Huh.
can just have a preview of what was done so that if new joinees are there, they'll be able to understand.
So till now, actually, we have seen like why we need verification, what is pre-silicon verification, and what is the process of building the test cases or identifying the test cases, building the test benches, and then finally the simulations. Okay, so we are talking a lot about simulations. So pre-silicon verification is nothing but more like simulations only. So we will try to understand what is simulation and how the simulator works basically. Okay. So the simulation is always done through the HDL code, right? So whenever you are doing a simulation, basically you compile the code and then you simulate, right? So when you are saying compiling the code, again that compiling of the code is broken down into the two parts: parsing and elaboration. So in parsing, first of all, the HDL code is checked for syntax and semantic errors. Semantic errors like if you have missed some semicolon or some signals are undefined and things like that. Basically, the correct syntax. And in elaboration phase, the simulator resolves the hierarchy of the design by instantiating modules, entities, and linking their ports and signals, and creates a data structure for the entire design. So usually in any complicated design, there will be a top module. Inside that top module, multiple modules will be instantiated. Again, in that multiple module instance, there will be number of small modules instantiated, and whole hierarchy of the design will be created in the HDL. So now it is elaboration phase which takes care of flattening that hierarchy. So it will resolve all the hierarchy. It will create a list of signals which are connected together with their ports and signals, and it kind of make a flat data structure which will be easier for simulation later on. So this is what is done in the elaboration. So any missing components or incorrect definition of the signals, all these get caught into the elaboration, because at that time the elaborator is making sure that uh, all the components hierarchically instantiated are flattened and connected well to each other. Okay, so this is about elaboration. Now, when the elaboration phase is complete, you have a flat hierarchy, flat data structure. So you will have a list of signals and list of connections. So similar to something to the net list actually. And then so that there will be a huge database created. And then in the simulation phases, first of all, you initialize all the variables, signals, registers to their default value. Then simulator sets up an initial event queue which includes all initial blocks or processes that must run at 0 time. Okay, so initial blocks basically, and even if you have a always block, at 0 times it is once executed. So what are the things involved in the initial block? What signals are involved in the always block? A list of all those signals is already made. Now you have to initialize them by assigning the default value, and most of the time it is 0. Okay, unless you mention the initial value when defining the signal itself, all the values are 0 by default. So initial value will be assigned. In some cases, if it is a wire or something and you did not assign any initial value, it becomes x, which is its default value. But some value is assigned to all the signals, all the variables in that whole database, and then it starts the event driven simulation. So how the event driven model works? So events are what? It is nothing but the change in the signal value. Okay, so if even in any case there is a change in any of the value, it is considered as event. Okay, in any signal value changes, it is an event. And for all that purposes, the event queue is maintained. A list of events that should occur is created. A list event scheduled to occur at specific simulation time. So that event queue is created when what signal is going to occur, and chronologically order is maintained, and then every time that particular time is lapsed, again the whole related signals are evaluated. So we will take an example for that, and then once that event queue is occur at 0 time, say all the events are completed, and now next event is scheduled, say at after 5 nanoseconds or 5 units of time, then the time advances to that particular time. Then again for that time, again the list of events is created, the event queue is created, and according to that event queue in chronological order, all the signal values are again updated, and it will check whether another event is generated or not. If no, then it proceeds to the next time advancement. And this is how the simulator works. So we'll understand with this example. Small code is here. So the module is defined. You have wire A, register BC, and register D. Okay, and then there is one assign statement over here. Assign A is equal to B and C. So this is one statement, and then you have an always block, always at A, D is equal to B or C. Then you have two initial blocks. One initial block for kind of a test case, and another initial block for the clock. Okay, so the clock is created by using this forever loop. So now how the simulation is going to happen? First of all, this hierarchy is created, flattened hierarchy in elaboration phase. So it will understand that the data structure will have these signals A, B, C. It will understand that this A has dependency on B and C, and this D has dependency on B and C. And then B and C will be evaluated when there is a change in A. That's how that elaboration will take care by creating this database. So it will create the order sets by which it has to do the evaluation. Now at 0 time, all these things are evaluated once. That means what? This A is assigned B and C. So initial values for B and C are assigned. Now B and right now there is no value assigned to B and C. So those are say XX at 0 time. So E is also X. And there is a change in this always block because A is having some unknown value. B and C is evaluated. B D is equal to B or C. C and B and C both are unknown, so D is also unknown. Now we will go to the initial block. Now at initial block at 0 time, B is equal to 0, C is equal to 0. And then there is a wait for 5. Okay. So now there is no more evaluation to happen in this particular block. So it will go to the next block. In the next block, you have clock generated. So clock is assigned 0. Then it will go to the begin part, and clock is assigned not of clock. So clock becomes 1. Okay, so this is happening at 0 time only. And then there is a hash delay of 5. So now it has to wait for 5 units of time. So the whole again, so again this whole database will be evaluated to check whether any other events had occurred. Now because this B is equal to 0 and C is equal to 0, and we have this statement as A is equal to B and C, that this statement has to evaluate again. So now it will create A is equal to 0 because B is equal to 0 and C is equal to 0, A is equal to 0. So now A has changed from unknown value to A. So now again this loop has to be executed, this always block. It will see that, oh, there is a change in A. So this is one more event. So let me evaluate this statement after that always block. So D is equal to B or C is also evaluated. And now B is also 0 and C is also 0. So D is also 0. So now the D becomes 0 from X. So at 0 time, what you will observe, A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0. All are 0, 0. So initial, now the evaluation will have, now no more events are getting created because of these changes. So it will directly wait for this 5 time units, and then this it will evaluate this B is equal to 1. Okay. So now B is equal to 1. With this value, again, this whole thing is evaluated because there is no change over here. There is no change over here. No, there is a change, right? B is equal to 1. So this assign statement has to be evaluated again. But C is 0. So A is equal to 0. So this always block will not be evaluated. Now then again it has to wait for 1. By then it will check that 5 time slabs 5 time unit labs has been done. So it will again assign the value clock is equal to not of clock, and then it has to wait for 5. In between there is 1 over here, right? So after 1 time unit it will execute this particular statement like C is equal to 1. Now is it going to make any difference to A? Yes. Again, this assign statement is executed and B and C is equal to 1 is executed. So A has now become 1. Earlier it was 0. Now it has become 1. So again, this always block is also executed. And then B gets value 1 or 1, that is 1. So after 5 plus 1, that is 6 time units, this D will have value equal to 1. And both B and C will be having values 1 and 1. And after that, what happens? Now this initial block is over. There won't be any change in B or C. Then again, after 5 nanoseconds, this clock will be assigned not of clock. Is there any change? No, there is no change. So this forever loop continues and the clock will get generated, but there won't be any change in any of this. So I hope it makes clear how the simulation happens. Okay, so like that, now we have taken very small piece of code, so it is easy to explain each and every event and its evaluation, but in very complex thing, it becomes a complex process. And also one interesting thing is in the beginning, we have seen like multiple times this evaluation is done at 0 time only, right? So each time that whole design is evaluated, it is called as delta. And at 0 time or at any single point of time, there could be multiple deltas of execution that can happen. So that is called as delta delay. So time has not progressed, but evaluation has happened once. So that is one delta. Then another evaluation happens. That is another delta. So the difference between the two deltas is delta delay. So it is happening at the same time, 0 time lapse, but delta delay. So you would have heard this term maybe sometime less delta delay. So this is what is a delta. So I hope this is clear now how the simulator works. And with these simulations now, the waveform is created by the some stimulus generated. Basically, all these timings and the values are recorded by the tool itself, and some vector file is created, and then the waveform generator reads these files and it creates the waveform. Like at this time, this is the value for all the signals. For this time, this is the value for all the signals, like that. And also in the simulation process, you can see some textual output which you are giving from your display messages or from assertions and monitor statements, like that. So you will create also the logs. So the simulation will have at least two outputs, waveform and the log. I hope this part is clear. So we'll go to the next. So this is how actually the waveform will look like. I have tried to put it by hand. So here you see, like, after 5 nanosecond that B has changed first. Then after that, after 1 nanosecond, C has changed. And after C has changed, at that time, A also changed. Because of the change in A, D has changed. And after that, there is no change. So manually, if you try to record these values like this, you can also create the waveform by your own. And the simulation, the waveform will look something like that. This is some other waveform, not for our design, for example, we have taken, but this is how the waveforms will look like. Okay, so to understand the further process, we will take an example. We will take the example of a SRAM. Okay, so this is a SRAM. Note that it is not SSRAM, there is no clock. And this is a functionality. So I will keep this slide as it is. You can read it for a minute or two. I'll wait till then. I hope you got enough time to go through this description. So basically, this is a basic SRAM. It has CE as chip enable and OE as output enable. WE is for write enable. OE is for write, OE is for read. And there are two enables, BLE and BHE, which will enable either the lower 8 bits or higher 8 bits. Also, you can assert both BLE and BHE so that the entire IOs from 0 to 15 are selected. Data width is 15 and address is 18 width, 18 bit wide. Okay, so you have A0 through A17 as address and IO 0 to 15 as IOs. So this you can consider that IO you can consider it as a data bus, and this A is your address bus. So basically you give a address and chip enable, and then either you do write operation by asserting WE or read operation by asserting OE low. And BHE and BLE for the byte select. So this is a truth table for that. It describes the functionality by each pin. So here it is clear when CE is high, nothing can work because everything is in deselect mode, power down mode, and inputs and outputs are high Z, high impedance state. So to perform any operation, basically CE has to be asserted. Then if WE is asserted, it's considered as read operation, but read will not happen unless OE is low. And for byte select, there will be, or half word select, there will be like BHE and BLE, byte select only. Yeah. If BLE is asserted, then lower byte is selected. If BHE is asserted, higher byte is selected. Both are asserted, then the entire data bus is selected. And the write and read happens accordingly. So this is a truth table. You can take a while to go through the truth table once again. I hope you have enough time to go through this truth table. So we'll proceed next. So this is how the simple SRAM pinout will look like. This is what you see on the chip. And the corresponding HDL module will look something like this. There will be input wire, WE, OE, BHE, BLE, address, all are inputs. This is memory. So address and control signals are going to be input, and only one output, that is also in out, which is a data bus. So what will be the test scenarios for this? So there has to be a write operation where we assert CE, W is asserted, address is assigned, and data is assigned from IO 15 to IO 0. So this will be a simple write operation. And then you also can have similarly the read operation. But we have to see whether is this a right sequence which we have given. Like first of all, you assert the CE, then WE, and then address and data is asserted. Is this correct? After you assign the address and then you change the data, then your setup and hold is not going to meet, right? So data has to be stable before the CE is asserted or address is assigned, right? So your chip select is going to be the one which is going to control the device, right? So first of all the data kind of signals needs to be driven. So first data is assigned some value, address is assigned some value where you want to write. Then you assign the CE and then you assign the WE. Then this is the right sequence of operation. What will happen when you assert the CE first? The data will become unstable and it is going to affect the functionality. It may violate your setup and hold requirement because CE is already asserted, right? And in this case, there is interesting part how when the actual write happens. So it is important to go through the timing diagram as well. Just going through the functionality is not enough. So what is written over here? First of all, you can see the address which is being asserted. Then CE is asserted, WE is asserted, that is made low. BHE, BLE is asserted, and data is also there. But here actually it is showing like after CE is asserted, then data is changed. So is it allowed? The timing diagram says it's allowed. Okay. So what are the important parameters you have to see with respect to what? That there is something called as TSD and THD. So TSD is a setup time for data and THD is a hold time for data. So with respect to what this setup time and hold time is shown, it is with respect to this WE edge. When WE is deasserted, at that time the data has to be stable. So whatever you do over here doesn't matter. What is important is this point. When WE is being deasserted, at that point we have to make sure that data is stable. C is still being asserted, so that is not mattering much, but you are deasserting WE and write is going to happen on this edge, positive edge of WE. Okay, so with respect to this edge, this data must be stable. As long as you are assigning the data well before even the C and WE is getting asserted, that is going to be the right functionality. Okay. Similarly, you can have function CE controlled write cycle. That means write this WE is still low and CE will go from low to high and W is still low. Then the write will happen on the passage of the CE. That will be CE controlled cycle. Okay, so accordingly, you will have to write the scenario. So what should be the correct scenario? The address is assigned, CE is asserted, W is asserted, data is assigned, and WE is deasserted, and CE is deasserted. Only then your scenario is going to get completed. If you just assert and then keep on changing address, you may not be able to write anything onto the memory. So you have to make sure that the correct operation is done, and it is done completely by looking at the timing diagram. So unless you deassert WE, write will not occur. So the complete test scenario will be assigning address and data, asserting as CE and WE, and then deasserting CE and WE. Anything is missing here? Have we missed any signals? Yes, BHE and BLE. What if both BHE and BLE are not reasserted? You will not get any data written, and you will not get. You will you will start thinking why the data is not written, even though I am done everything correctly. So you have to ensure that BHE and BLE also. So you have to make sure when you are writing a test case, all the inputs are taken care of. No input should be left without assigning any value or giving attention to the inputs. All the inputs must be attended. So once you assert both BHE and BLE, then the whole data from 15 down to 0 will get written into the memory. And that has to be asserted before that deassertion occurs. Okay, so if you have to write a correct sequence, that will be like this. Address assigned, CE asserted, BLE and BHE asserted, WE asserted, data assigned, when WE deasserted and BHE, BLE deasserted, CE is also deasserted. So it's also important to deassert the things, deassert the control signals. Otherwise, you may run in some erroneous scenario. I hope this sequence is clear now. How precisely you have to define the test case. If you don't define the test case precisely, you will not implement it correctly. So you will see that there are three types of write scenarios: WE control, CE control, similarly BHE, BLE control also. So when you are asserting the BHE or BLE and deasserting BHE or BLE, then the write will occur at the passage of BHE or BLE at their for their respective datas, respective bytes. Okay. So there is no simple only write and read. There are three types of writes: WE controlled, CE controlled, and BHE, BLE controlled. Similarly, we go for a read operation. In the read, what we have to do is address is assigned and data should be tri-stated from outside of the memory module. Okay. That means now you want to take the data out from on the data bus. So from the test bench, you have to tri-state those outputs or the which are data in case of write. Then assert CE. Then WE has to be inactive. So if you had done the write before read, then you have to make sure that WE is deasserted and again make BHE and BLE as active. Then OE is asserted. So data should appear on the output bus. If any of this step is missed, you are going to get the erroneous data. So you have to ensure all inputs are attended again, make sure they are in right state, and then you check the output. Also, directly can you check the output at as soon as the OE is asserted? That we have to check from the timing diagram. So the timing diagram here for the data shows, read shows some certain timings. Okay. So there is some one timing over here, TDOE. Okay, so that is going to be how much time it is going to take for this when this OE is made low till this data is valid. That is called as TDOE. Again, there is a timing over here, TACE. How much time it requires from chip select low to data to be valid. Okay, so those are the important timing parameters. So you have to make sure that you sample the data over here after this TACE and TDOE are lapsed. Only then you are going to get the valid data. Till then, the data is not stable. And if you sample there, you will get some wrong data. Similarly, there are timings for TLZ and THZ. Okay, so for BLEs also there is some timing. So you have to make sure that all these timings are met and you are sampling at the right time. Okay, only then you will get the right data. Also, there are other parameters like TPD. What is the minimum time for CE to go high? What is the time after which the data will remain valid after the CE is deasserted or OE is deasserted? So all these things, timing parameters also you will have to take care when you are doing a write or read operation. Okay, so now here you see this read is controlled by OE. If you see here, it shows after OE is asserted how much time data is valid, and after OE is deasserted for how much time data is valid. So it is not depending on the CE or address over here. It is mainly the data validity is mainly depending on the OE over here. Obviously, if CE is deasserted, your data is going to get high Z, but we are mainly looking for OE controlled read. Okay, so one thing is OE controlled, and there will be another type of read cycle where actually OE CE remains asserted and only address changes. What will happen then? The data will appear from the another address. If OE has made low only over here and CE is also not deasserted and the address changes, then from this address change another data will appear, and then you will have to look at this timing parameter address change to data. So that will be the address controlled read cycle. So you see here two types of read, single read or CE controlled or OE controlled, and then you have continuous read that is controlled by the address. So CE and OE are continuously asserted and only address changes. For write, that doesn't happen because write will happen either on passage of CE or WE or VHEVLE. But for read, continuous read is possible. You just keep on changing addresses and the different data will appear. Okay, so for read operation, what we have to do? Address is assigned, then CE is asserted, WE is inactive, that we have to make sure. VHE, VLE are active, OE is asserted, data should appear, and then change the address. Then again another data should appear. So this scenario is for the address control read. So just to simply check one SRAM, basic with the basic one data and one address, you will have to go through so many scenarios. There are 5 scenarios we have identified: CE controlled write, WE controlled write, BHE BLE controlled write, and CE controlled read and address controlled read. So those 5 possibilities are there to do the write read operation. Now we will see how the SRAM test case has to be written. So till now we have just seen what are the scenarios for reads and writes. Now how the test case should look like? So the test case should have to do the perform write operation with address A is equal to 0 and data is equal to 0. Perform say read operation with address A0 and check data with which appears on A15 to A0. And okay, the data appears on IO15 down to 0, and repeat all above steps for n different addresses. So this is the basic minimum scenario for writing a simple test case for SRAM. But is this enough? Think for a while whether it is enough. So you are doing a write operation with A0 and data T0, perform operation with address A0, perform read operation, and check whether data is correct on I0, on basically the IOs. What could go wrong? Is this sufficient? Obviously no. Why? What could go wrong? How do you ensure that data is really getting retained in the array, or data in data buffer is getting put back onto the data bus? If really there is no array inside and whatever you are writing into the memory, it's simply getting stored into the data and the data buffer inside, and it's simply getting put out onto the IOs. How will you ensure that this is not occurring? So in this case, suppose you write A0 on D0 on address A0, and then simply you write read address A0. then whatever was written is getting stored just on D0. Then you choose some address A1 and write the value D1 and again read on the A1. Again, the data is stored in the buffer and the same data is getting outputted. So there is, even though there is no real memory there and simply data buffer is there, all the writes are happening to that same data buffer and all the reads are getting outputted only from the data buffer, and still your test case will pass and the bug remains inside. So to ensure that such bluff is not getting created, what we have to do, we have to add something more. So at least 2 different addresses you have to write sequentially, and then you have to read those 2 different addresses at least in a sequential manner again. Then if you write some data on A0 and write some data D1 on A1, and if there was a buffer inside, it will return data D1 for both A0 as well as A1. Whereas if the actual memory is present, only then it will return D0 for A0 and A1 for D1. And now these sequence needs to be needs to be done for n number of times. Only then you will make sure that test case is correct. And all these steps you need to be performing for different addresses and data. Is this point clear? I hope this point is clear, that where you can make a mistake. So always when you are thinking from verification point of view, you have to be a devil's advocate and think what could go wrong. So is this sufficient? Yes, but what should be the n number? So how many times you will check this? Now in this case, in our test case, there are 256 k locations. Can we really check for all 256? No, then we have to take some other thinking, right? So be a devil's advocate and ask different questions. What could go wrong? So one other question is, what if the internal array is of only 1 bit and the bug will still remain and errors will occur for all 3 upper bits, right? So what if there is a typo and do some other random array width defined? Okay, so say the case only there are 2 different addresses available and whole data is getting stored only with 2 addresses sequentially. There is a problem, right? Similarly, for the address bits, if any another number of address bits are given, say you are expecting 256k memory, instead of one bit is lost, and then you have only 128 kb of memory. So only half of the memory, and still you will get the correct data every time you write different addresses and read different data, right? So still this is not sufficient. And this can happen because of the typo for any random variable. Instead of 256, you have made 128k, or you could make it 64k, or even less 32k. So how will you figure out exactly how many addresses are present? Really, the address width, the memory array instantiated is of 256k. So for that, one thing is, write all the 256k locations and all the data to be written from all 256 locations. Continuously write for 256k and then read for 256k. But the problem is, there are only 64k unique data, right? Because what is the data weight? It's 18. So 2 raised to 18 is only 64k, and you have to verify the 256k locations. So some data will get overwritten, and then again there will be a problem. We will get out of unique data, and you will not be able to validate the memory completely. Plus, serial data is not useful. Why? Because the address is loaded as data, then what? There could be a goof up, right? And not actually the memory, not actually the data stored in the memory, but just the address is given out. Then also this will go wrong. So sequential data is also not useful. So what to do? So even though actual time for testing the memory chip can be fast, in simulation it takes a lot of time, and verifying all the time will be too much of consuming, right? So now if you place the memory actual after the fabrication is done and you want to read 256K locations, it will be done in very fast because you are running at very high speed. The propagation delays are in some nanoseconds, so it is running at some 100 megahertz. So reading all 256K locations will be very fast when you are actually doing the read-write operations onto the physical chip. But in simulations, it's going to be a nightmare. Say it takes only 20 milliseconds to do write and read operation for one simulation cycle. In 1 second, you can do only 50 accesses in simulation. And that means for 256K locations, you will have to do 512K accesses, that is 2.8 hours, just to verify your 256K memory. 2.8 hours is not the economical way of verification. Just your resources are being used just to check, make sure that one small memory is getting verified or not. And imagine what will happen if there is a 4 GB of memory. It will take around 3 months to run complete one simulation, and it is just not possible. How much energy will be consumed for all that? How much time, man months you will lose? And what happens after the 3 months? You find like okay, one there is one error while reading. Then again you have to repeat the whole thing for 3 months. Surely not. This is not the right solution. So what we have to do? You have to think about some other ways in which you can verify it in a better way. So if one very quick and simple solution is walking of 1 on the address bus. So what does it mean? That insert one at the end, and all 18 bits of address you make it as 0, and then keep on walking that one, shifting left that one from 0th position to whatever is the MSB position. Perform all the writes first on these addresses, and then read data from all these addresses. So in only 18 different accesses, 18 and 18, 36 accesses, you will scan the entire memory, and you will make sure that the correct amount of memory is being instantiated. There are no typos. Okay, so with this 36 accesses, entire 256K locations can be verified. Similarly, you can do the walking of 0. Insert 0 at the LSB and keep on shifting that 0 from LSB to MSB, and make sure that all the addresses are written first with all these different 18 locations and all the different reads then. Okay, so this is a quick way of making sure that the memory is getting written and read correctly. Also add first and the last address in the list of addresses so that the corner cases are also covered. So this could be one solution. But does it happen in reality? Like anybody is going to access a memory like this? No. Absolutely randomly the address will come, random data will be written, and some random sequences of write and read happen. So we have to ensure that this random sequence we are able to generate with the test bench. Okay. So you need the random generation, and we have to make sure with this random operations also your memory is working correctly. And these addresses and write reads cannot be absolute random. There has to be some rules followed, right? Because the addresses which you are giving should be within the constraint. There should be some meaningful addresses. Okay. And the operations also has to be in the combinations of writes and reads. Okay, so you have to have some rules to be set for generating these addresses, this data, and the write read operations. So those rules are called as constraints. Okay, and that's why you go for HVLs from HDL. So these HVLs provide good solution for generating the random data as well as good constraint solvers. So there are some constructs in HVLs which are called as constraints. And if you write the proper constraint, by default there will be a constraint solver available with the HVL compiler simulator, which will solve all the constraints and will generate the values within applying all those constraints. So we go for HVL. So what will be the components required in the test bench? So there will be a generator, a driver to drive. So now we have the scenario, right? We know in what manner the data has to be, the signals needs to be created. We know what kind of data we want to provide, how to extract the data from the data bus, what things need to be taken care of. And also we have to provide the reference model to compare with, like what to expect from the output. So all these components, we have the list of requirements. We have a generate, which will generate random or directed address data and types of generation. Then you have a driver to drive all the signals in precise sequence. Just randomly you cannot drive the data. You need to follow that sequence which we have created now. Then you have to monitor the data and extract the data at correct time from the database. Then reference model to store the data within the memory and provide the expected data during read. Okay. So we have to know what data to expect. When you are generating the random cycles, random address and random data, we have to make sure that we have the correct information available in the test bench to compare with. Okay. And finally, the comparator to match the data which we have received from the memory and from our own database, that is reference model. And scoreboard will keep count of how many times data matched and how many times it does not match. So these are the requirements of the test bench: generator, driver, monitor, reference model, comparator, and the scoreboard. Okay, so and finally the test case will decide what kind of test scenarios you want. Okay, so now how to write the requirement for each of the block. So say we have one config as an input for this generator and address data and transaction type as output. And what is the functionality of this? The generator can be configured to generate a walking of 0 or walking of 1 pattern, or can be configured to generate random address and random data and random read write sequences. So accordingly, address data and read write cycle will get generated. And the transaction type also should be one configuration parameter, which will include 3 types of writes and 2 types of read. So this is a type of generator. So this is the code, how it will look like in HVL for the generator. You can go through it quickly. So here I've made use of some HVL constructs like enumerated logic, which we are defining to define types of reads and writes. Then we are defining here the memory in the test bench, and then random, and then you have this here the generator function to generate the transaction. Then we want to have the driver. So driver will accept address data and transaction type, and it is going to drive all the signals actually onto the data bus, taking onto the DUT, taking care of all the timing diagrams. And there shall be 5 transaction times, 3 write and 2 reads. So this, according to the input parameters, this driver should be able to generate all types of reads and writes by creating correct timings according to the timing diagram. So the generator is only going to generate the data, what to write, where to write, and whether to write or read. And the driver is actually going to drive the signals in the required fashion onto the DUT. Then we have the monitor, which is going to monitor all the inputs and outputs of the IO, and depending on the exact timing diagram, it has to extract the data and address at correct timing. When the read operation is happening, at that time only it should sample the data bus and address bus, and it will capture it and store it inside or pass it to the scoreboard. And at the same time, our reference model is also getting the address and data and read write type, and it is going to store the data accordingly. And when read is happening at that time, it should give the data out and the address. So the comparison can be done. Okay, so these are the requirements of our reference model. And comparator will take address and data and expected data from the reference model, actual data and address from the monitor, and expected address and data from the reference model, and it will do the comparison and will tell if the test case is pass or fail. So the test bench will look something like this when stitched together. And then test case is going to control what kind of scenario you want, whether you want a random scenario or walking of 1 or walking of 0. That will be done by test case. And finally, the output from the comparator will be given to the test case, whether test case is pass or fail. So it will keep record of that. So now test case becomes simple. It will only have to configure the generator and driver, and if anything else is required. Okay, so this is how we arrive at the typical test bench structure. And you know now what could be the code for each one of these components. So are we done with the test bench? So even though all those things have been taken care of, we have to also think about the invalid scenarios. So what if the data appears even if CE is not asserted? What if data is getting returned when CE is not asserted, or output changes when CE is not asserted? Then it's wrong, right? So we have to make sure that what is not has to happen should not happen. We have still till now we are expecting something to happen, and whether it is happening correctly or not. But something which is not supposed to happen should not happen. That is also a part of verification. If DCE is not asserted, write operation should not occur. The CE is not asserted, the data on the database should not occur in case of read. So all these things are also required, and this these will get caught with data integrity if the scenario of that type is included in driver. But otherwise, for such rules to be followed, we need a protocol checker. To detect any illegal activity, that what happens to be detected earlier, protocol monitors are required. Okay, so in this case, what can be done? Data should not change when WR is high and CE is high, even though OE is low. So this can be a protocol rule. When WE is high and CE is high, in that case, OE should, and even though OE is low, data should not change. That will be one rule, which can be written in form of assertion. And in the write cycle, data address should not change after CE is asserted. That could be another rule. So these are the kind of rules which you have to make sure that any illegal activity is not happening. So if you have the assertions based on these rules, you can detect very early stage that there is something illegal happening. So for that, this you have the assertions. Till now, data read and write is good for data integrity. But to make sure that the correct rules or the timings are performed, the right kind of scenarios are happening, basically you need the protocol checkers. Now we have been keeping continuously now whether it is enough, and always the answer is coming like no, still we are not done. So when to stop? And this happens actually when if this design is quite complicated and you keep on verifying it, you keep on coming across different scenarios, you keep on adding test cases, or the bugs also may get popped up, even though if you think that you are close to the verification and the verification process doesn't end. So what are the criterias for stopping the verification, when to stop the verification? So the two main criterias, all pre-identified test cases are passing and coverage goals are achieved. So what is coverage? So with random testing, this it's very important, one parameter comes up, that is functional coverage. And in any case, the code coverage has to be attained 100%. So what is code coverage? That is to check all the implemented code has been triggered. Okay. That is usually done automatically by the tools. You just have to give one command line option. It will automatically check when you are running the test cases whether one particular piece of code has been triggered or not. And functional test cases, functional coverage has to be obtained by writing coverages into the code itself. There has to be a separate code to be written, functional coverage code, and that is the constructs are provided by the HVLs. Like in system Verilog, there will be some constructs to get the functional coverage, but separate code has to be written for functional coverage. So in code coverage also, there are different types like line coverage, which will make sure that all statements or blocks are covered. Then there is a expression coverage or the conditional coverage. So each expression in the code will be evaluated at least once to true or false. And in conditional coverage and expression coverage, it is also made sure that each type of like the expression is evaluated in all possible ways. For example, there is a code like C is equal to A or B, then C has to be that A or B has to be 1 at least once, and A or B has to be 0 at least once. But apart from that, it is also checked that that B or C is becoming 1 because B is 1 and C is 0, and also B is 0 and C is 1. So all kinds of expressions are all you can say different ways in which that expression can become 1 and 0 also is checked whether it is triggered in that fashion or not in the expression coverage. And finally, we have to see that all the signals which are defined in the HDL code are toggled at least once. That is called as toggle coverage. So it has to toggle from each signal has to go from 0 to 1 and also should come from 1 to 0. Both the ways the toggle should happen. Only then that signal will be completed as considered as 100% complete. So that is a toggle coverage. And in functional coverage is required mainly for the random verification, because in random verification, you are generating the scenarios randomly and then you don't know what kind of data you have generated, what kind of sequence you have followed. So it becomes very important to make sure that the interesting scenarios are covered. And functional coverage is the only way to check whether the expected scenarios are happened or not. So whenever you are doing a random verification, your completeness can be monitored only through the functional coverage. And in functional coverage also, there are different types like value or range coverage, transition coverage, cross coverage. So in our case, value range means we will cover whether all the ranges of the address are covered or not. Like from say lower to lower 128K and upward 128K, both are covered or not. Then is there a transition happening like write, read? Are there transitions happening like write, read? So whatever number of transactions you are interested in, you can put in the transaction coverage. And cross coverage also, like with address and write or read. So for one particular address, whether write has happened and also read has happened. So you can do cross of read write plus address range. So that will give you the cross coverage. So these are the types of the functional coverage. After you are done with all this verification at the RTL level, later on you will have to move into the synthesis. And after synthesis, you, as I talked earlier, you will get a netlist generated. So at netlist level also, you will have to again generate the again do the verification. And at this point, mainly what we are targeting is to check there is no X propagation, like any signal is going because of multiple drivers to S, or it is uninitialized and hence it is becoming X. So once the X insert, like unknown condition get inserted into the design, everywhere that X will get propagated and finally you will not see anything but X. So it is very important to make sure that you do the netlist simulation mainly focusing on X propagation, like there are no X's seen anywhere. Also at the end, you get the back annotated netlist and with the timing information. So you have to make sure that there are no timing violations. So two things are important in gate level simulation: X propagation and timing violations. So the same test bench you have used earlier, if you have written in a good manner, not depending on any internal signals and all, can be utilized for the gate level simulation also. There is also one more thing as formal verification. So as I talked about earlier, as like for assertions. So assertions are basically properties defined for the design. So the design has to adhere to certain rules or properties, and those properties are written in form of assertions. And those rules must be followed by any design. And if entire design can be converted into such properties, a formal tool can check if the design is mathematically correct or not. Okay, so there are mathematical ways to check whether those properties are validated or are valid or not. Or means the design is following all the properties, that means it is functionally correct. So no need of simulations. So this is called as formal verification. So you define the design in terms of rules and mathematically prove that all those rules are followed entirely by the design, and hence you need no need of simulation. By mathematically you can prove that the design is correct. This way of verification is called as formal verification. There are no simulations required in this case. But the assertion can also be used for simulators for protocol checkers. Okay. So the same assertions you can use, or you can write some additional assertions for rule checking. So this is all about the verification. I hope many of the things are being clarified in this case. If you have any questions, then you can ask.
Yes, participants, you can pose the questions or you can unmute yourselves and ask the question. Any questions from?
Doshi ma'am, just unmute yourself. I have unmuted all the participants.
Yeah.
Gokul ma'am, also you are also unmuted. Muted
Now
actually.
I have unmuted myself.
No, she is unmute.
If you have no questions, then I think we can stop.
Yeah.
Yeah.
And the session was really wonderful. So it's time to pay vote of thanks to the esteemed guest of honor for today's ATAL FDP on pre-silicon verification of semiconductor device. With over 25 years, extensive experience spanning verification, strategy definition to functional verification closer, your insights were both deep and highly practical. The expertise in verification planning, test-bench architecture, HDL, HVLS, that is VHDL, Verilog, System Verilog, and methodologies such as VMM, along with hands-on exposure to ABMA protocols, it greatly enriched the learning experience, ma'am. The real-world perspectives drawn from working with global teams across India added a valuable industry dimension to the session. So, on behalf of the organizing committee, we sincerely thank you, ma'am, for sharing your vast knowledge, global experience, and technical excellence, making this ATAL FDPA session truly impactful. So, once again, heartfelt thanks for the time and the opportunity given to help the faculty members understand the practical views of whatever you shared it very well, ma'am. Thank you once again.
Uh, Thank you very much, ma'am, for your wonderful session. Before you leave, there is one question in the chat box from Prashant Deshmukh. Okay, so I will just read the question. Can you take test vector from the file and apply it as input to test bench?
Yes, so I have just answered. Yes, that is possible, and sometimes it is required basically they do it in the EDA tools, any EDA tool vendors. So as I mentioned earlier, that whenever you are creating the waveform, basically it's nothing but the record of at what time what value the any signal has, and You can very well extract by reading those vectors. If you have the right tool to read that formatted text, you can read that file and you can write the driver to get the data from that vector file. So every signal you can assign the values which have been generated earlier at correct timing and regenerate the scenario. That is very well possible. And that is mainly done by the EDA vendors to debug the test case which is given by their customers.
Okay, I hope.
Yeah, he got an answer. Thank you, ma'am.
For what you need component to read file and create driver. Okay, that is the answer.
You have answered that.
Okay,
Yes.
thanks.
Okay. Thank you once
Okay,
again.
thanks for giving me the opportunity to share my knowledge with others. Thanks a lot.
Thank you. So without wasting a moment, let's have hands on together for our next speaker, the last speaker of this FDP, Dr. Pranav. Are you there?
Yes, ma'am.
Okay. So it's time to introduce our esteemed guest. So it's my pleasure and privilege to introduce today's distinguished resource person, Dr. Pranav Pawar, who is currently serving as an assistant professor at College of Engineering, Pune Technology University. Dr. Pawar has a strong academic and research foundation, having completed his PhD and postdoctoral research from IIT Bombay. He holds an MTech in nanotechnology from VIT University, Vellore, and B in Electronics and Telecommunication from SPPU, giving him a rare interdisciplinary perspective that seamlessly connects electronics, material science, and emerging quantum technology. His expertise spans nanomaterials, graphene based devices, energy storage, water purification, flexible electronics, and notably quantum dot based sensor technologies. His work on quantum dots and low dimensional nanomaterials is particularly relevant to today's session, as these materials form the backbone of many next generation quantum devices, sensors, and nanoelectronic systems. Dr. Pawar has an impressive research portfolio with publications in reputed international journals such as Nature, wow, the number one journal, then Materials Today, JOM, Scientific Reports, and the Journal of Power Resources. His research is well organized for translating fundamental science into scalable and impactful technologies. He is a recipient of several prestigious awards and grants, including the IC Impacts Excellence in Academic Award through the University of Alberta, Canada, and the DST Nidhi Prayas Grant and the Young Scientist Award. He has also received Best Poster and Innovation Award at ACES 2023, reflecting his contributions to both academic excellence and innovation. Beyond research, Dr. Pawar is deeply involved in teaching, mentoring, and delivering invited talks, inspiring students and researchers to explore emerging frontiers of science and engineering. So, today's session, titled Introduction to Quantum Devices and Exploring Horizons of Quantum, is perfectly aligned with Dr. Pawar's research journey. His experience in nanomaterials and quantum dot based sensors provides a strong foundation to understand how quantum principles are shaping future devices and technologies. We are indeed fortunate to have Dr. Pranav with us today. Again, I am very much proud, and we again hats off to Dr. Pranav because he's our alumni, and we are really proud of him. I'm confident that his talk will offer valuable insights and broaden our perspectives on the exciting world of quantum devices. So please join me giving a warm welcome to Pranav. Once again, thanks a lot for making our institute very proud of our alumni, and welcome. And without wasting the time, I would like to hand over the stage to you. Welcome, Pranav, and you can start.
Thank you, ma'am. Thank you for such a nice introduction. It's a privilege like to give presentation in my own college.
Can you be a little louder, Pranav?
Yeah, ma'am. Is it
Yeah,
audible now?
fine.
Okay, my screen is visible now.
Yes, all good.
Okay. Yeah. Good evening, all. So today's session will be so in this particular session we will be exploring the quantum horizon and introduction to
Little
the.
louder. Because we don't want to miss a single moment of what you will be exploring today. Yes, you can start.
Yeah, now it's okay.
Fine.
Okay. Yeah, so today we're going to explore the quantum phenomena. So as we recently have introduced to the quantum technology, but the race has started long back. Now here you can see the all other countries, those who are invested in the quantum world, like India just now has started with the $1 billion, whereas Canada has already invested 1.1 billion and UK has 1.3, whereas USA has around 1.2 billion. So, and the Japan and Taiwan, so they are almost 700 millions. So as we can see, all other countries have started long back in the 90s for their quantum evolution. But whereas India just now has started in 19th April 2023, central government has announced like they will be funding 6,003 crores for accelerating the quantum technology in our nation. So they launched this particular theme under National Quantum Mission theme. So our nation will going to cover quantum computing, quantum communication, quantum sensing metrology, and quantum material and devices under this National Quantum Mission. So this mission is very like it was already ICER Pune was already working on the quantum world before also. So they have declared like ICER Pune will be a hub for this particular National Quantum Mission NQM, and there they have established IHub Quantum Technology Foundation, through which we can able to learn the quantum technology from there. So either it will be of any field. So either you are working on quantum computing, still you can do the course there, or you can work on quantum material, quantum sensor, or quantum metrology. So all these courses you can able to do using in the iHub quantum technology. So iHub quantum hub technology, it will be a hub, and there will be different spokes where we can write the proposal for getting the funding from them, and also they are promoting the startup, those who are entering into the quantum field. So there are different application of quantum, so that's why we need quantum technology nowadays. So these are what different application which we can see. The first application is imaging. So imaging we can map to the different materials or different technology through which we can able to generate that particular data. Similarly, sensing, computing, and communication encryption, position navigation, and atomic clock. Whereas imaging we can easily get it through the either electron spin or through the photons. Definitely in the next slides we're going to cover what are the electron spin, what are the photons, and the sensing will be used for using all these characteristics of the quantum material. Whereas computing will going to use all the characteristics of the atom. Whereas communication and encryption will be using only photons, and the position and navigation timing will be using only ions, and for atomic clock only atom will be used. And all these different structures, or we can say a different quantum bits, can be used uh, for this particular application, which will be further embedded or using a certain material. For example, we can use a neutral atom, or we can use ion trap, we can use quantum dot or superconductors, or any two-dimensional quantum material, or NV center diamonds, or N type or P type of different quantum particle we can use. So these particular particles we can use for having this kind of qubits, which use further for these applications. Okay, so that's why we need a quantum field. So it's like quantum field will going to enter in each and every field in future. So definitely we must be wondering like why and what is this quantum. So before the quantum physics or quantum equations comes into picture, these are the few phenomena of physics which we can able to like which scientists were not able to produce or reflect in terms of a mathematics equation. So the first is like atomic absorption spectra. So this particular spectra is nothing but when we are shining a light on a particular gas, okay, or a particular atom, so they will give a certain kind of spectra for that particular atom. Like sodium has this particular kind of spectra, nitrogen has this kind of spectra, and from this we can able to find out these are what the spectra and this is what will be the atom. Okay, so like that it's a signature. So it's like we can say a test where we can give a certain energy and we'll check what's the map of it. Similarly, the second phenomena is like all of you aware of the atomic structure. So it's like a nucleus at the center and electron are revolving around it, whereas electron, so there will be a question like in sun and planets, so there is a gravitational force which keeps this particular earth to revolve around the sun rather than going inside the sun. Okay, so for nucleus also, center has positive charge whereas the electrons are negative charge. So definitely it's a question why these electrons or negative charge are not getting attracted towards the nucleus and fall into the nucleus. So that particular concept was not explained in that era. Then the third phenomena is black body radiation. Like any heated object has produce a certain kind of electromagnetic wave or electromagnetic spectra. For example, sun. Sun is has a huge lot of photons, or we can say electromagnetic spectra, which cover all the radiations. Similarly, other heated body also. So we called it as black body radiation. So why these particular radiations are produced and why it's covering the whole spectra? That answer was still not there. And the fourth phenomena, simplest one, is photoelectric effect. This photoelectric effect is nothing but we are striking photon on a metal and it throwing back the electron from the surface of a metal. Okay, so as during that era, we have considered photons or light is nothing but the electromagnetic wave, and why it's reflecting or it's knocking out a particle, okay, that is electron. So these questions were not answerable. So the journey has started long back for quantum. So it is starting in 1871 where Rayleigh scattering comes into picture. Dr. Rayleigh has discovered like when light or light is coming into the sky, so it gets scattered and we will see the light, the sky is blue in color. Then the second is in 1887 photoelectric effect, which we have already discussed. Then the next in 1905, the quanta concept was introduced by uh, Albert Einstein in his paper. So he has delivered, or he was saying, the light is nothing but a packet of energy which is coming from it. So it's not like electromagnetic wave which we are considering for those particular days. And then in 1923, quantum effect was discovered by Mr. Quanta. So where a photon is interacting with an atom, so it will knock out an electron and it will also generate a certain photon. So normally what we have seen, if you're considering light as an electromagnetic wave, so definitely it will generate output as a wave only. So that's what the concept. But why this electron is coming, that was not clear at that time. But whereas in 1926, Mr. Photon Lewis, he has uh, discovered, like he has already given concept like light may be acting as a particle and maybe as a wave, and so they called it as particular particle as a photon. And later on, the same paper was published in 1905 by Albert Einstein, where he has coined that particular packet of energy as a quanta. And then from there, the later era, we called it as quanta. And the technology which used that particular concept, like wave particle duality, we called it as quantum technology. Whereas in 1928, again, we have observed the Raman spectroscopy. So Mr. Raman has discovered like electromagnetic wave, which is coming and striking on a particular atom or a molecule. So that will going to generate a kind of a particular signature, and that signature we can easily interpret, or we can predict through this particular wave particle duality of photons or light. So the simplest experiment for the wave particle duality is nothing but what? The double slit experiment. So it's like the double slit where we are passing, or we have considered electron as a particle. So when we are passing particle in between the two slit or two those particular tiny holes, so definitely those particular particle has to uh, align where this particular hole is, like on the screen, where the hole is in front of the screen. So when a particle passing through, so it will going to accumulate on this side or on this side when we are consider electron as a particle. But the observation was totally different. So they were observing, even though we are passing electron beam through the double slits, but we are getting pattern of a wave rather than a pattern of a particle. So this what it proves, like electron is acting as a particle when we are considering our postulates or those particular atomic orbital theory, but the same electron is acting as a wave also. So during this particular experiment, so scientists got clear view, like electron is acting as a particle also, and electron is acting as a wave also. And definitely these particular electrons are further will be used in the atomic orbital theory and as well as molecular orbital theory, where we are arranging the electrons in those particular energy level, which you called it as n quantum number, which will be 1, 2, 3, where we are considering the s orbital, p orbital, d orbital, and f orbital. In those particular orbitals, those number of electrons will going to arranged. So when we are considering those particular electrons, so remember in our slide we have seen like previously when we are considering electron is revolving around the nucleus, and then while that electron is not going inside the nucleus, okay, because of opposite charge will going to attract. So these particular principles give uh, us the solution, like this is what the thing, electron is acting as a particle when we consider this positive and negative, but electron is also acting as a wave. That means electron will not going to fall into the nucleus of an atom. So when we are arranging these electrons in the orbits, so there are different types of quantum number which comes into picture. So the first principle is Heisenberg uncertainty principle, which shows every electron will going to occupy different energy level. So either it will be in the same orbit, but at least it will have the different spin. Okay, so that particular spin either it will be the up spin or down spin. Similarly, energy quantization is also there. So where we are saying like these particular electrons are arranged in the different energy level, and all those orbits will be fulfilled, and then the electron will be filled into the next orbit. Okay, so I hope this is clear. So it's like we are covering the small physics and little bit of chemistry to understand the quantum. So is it true like quantum theory was already discovered just now? So as we have seen in Vaisika Sutra, Kanath Rishi, in the Kanath Sutra, he says, like, so he has already discovered what is an atom. So when we are trying to disintegrating the bigger object into the smaller and smaller and smaller object, so what he has predicted, there will be the smallest thing, which we called it as Anu. Okay, so that's the same thing was further explained in Greek philosophy, where they called it as atomos, and nowadays we called it as atom. So Kanath Rishi has already discovered like what are the universe is there. So where the atom which we have found, or the atomic structure or the atomic structure contents are there. So those are the similar in a smallest seed of a fig, and it will be the same in the largest universe, bigger particle. Okay. So like that, he has said, like, so now we can relate it to the electrons. So the electrons which are in the fig, those are also negatively charged, acting as a particle and as well as acting as a wave. Similarly, the electrons in the universe, a bigger particle, so there also it contains electron and they are also acting as a same. Okay, but still we are confused, like why this quantum phenomena is observed only for those particular smaller particles, not for our macro particles. Like our human body is also made up of that, then why it's not that? So definitely there are certain phenomena which we can able to understand first, so that we can see like why this thing has happening. Quantum phenomena, so there are particle property like position, momentum, mass, electrical charge, weak hyperchain. Okay, so all these are the different properties of a quantum particle. And the first, the latest which we have discussed are the quantum numbers. So all these particular property are of a single particle. Okay, so these particles are aligned in a particular body. Okay, with the certain direction. So this we can say those particular each and every particle will going to have a certain impact on each other. So we called it as quantum superpositioning. So this is what the physical system can exist in a multiple state at the same time. So this we can easily understand, like sea has waves and we are considering a small dot or a small water molecule of that particular sea. So that particular water molecule, okay, where it will going to move, that we can predict by the all the particles movement of a ocean. Okay, and similarly the quantum, again the different quantum numbers are this. So we can say the quantum spin, boson spin, fermion spin. Okay, so all these are the different spins are arranged in a particular order. So they may arrange in randomly or they have effect on each other. So that's how they will going to cancel all these particular each other's properties, and they will give a certain superposition which we will going to observe as a single particle or a single property. Okay, so that further thing we can easily understand it through the quantum entanglement. Okay, so now we will just see, like as per the Kanad Rushi and the Atomos what they have discussed. So we'll just understand through a song. Okay, I hope the lecture will not get bored. Is it audible?
Yes, sir. No, sir. It is audible.
Yes.
No, sir.
Yes, sir.
Audio is not clear actually, not getting to the audience. So,
Okay, okay.
can you run one more time?
Yes, yes, sir. Yes. Still, it's not
Still,
audible.
not it's not audible. Respected Nathu sir, have the suggestion file sharing, click audio. Just check
Yeah, yeah.
by clicking that.
प्रणव सर, तुम्ही ते चेकबॉक्स केलाय की नाही? इनेबल ऑडिओ. इनेबल ऑडिओ बहुतेक केला नाहीये तुम्ही सर. शेअर करत असताना खाली चेकबॉक्स केलेलं नाही.
Yeah.
Falling in deep, know that would break uncertainty. Say, oh, electrons move too much. Slow down your pace and put that orbit on me. Come on now, follow my lead. Come on now, follow my lead. Orbitals take the shape they do, the stable states of the quantum rules. And when one approaches two, they combine and they're bonding. Thus hydrogen as a rule is found in nature as H2. Energy configuring a molecule, diatomically bonding. Low, high, low, high, low, high, low, high. Diatomically bonding. Low, high, low, high, low, high, low, high. Diatomically bonding. Low, high, low, high, low, high, low, high. Diatomically bonding. Energy configuring a molecule. When orbitals take the shape they do. One half spin will give a lepton a twin. One up, one down in the ground state. With S&P and quadruple degeneracy, the second shell can be filled up with 8. The higher angular power spread all the beautiful flowers and middle families that come into play. Well, here's a carbon with 6C. This ain't nothing tricksy, but we're gonna make some methane today. With hydrogen, it's like, oh, atoms, I feel your tug. Got my electrons bugged out, pulling on me. Come on now, settle around me. I'll hybridize to sp3. Say, oh, carbon, here's our touch. Spread out 109.47 degrees. Come on now, follow our lead. Come on now, follow our lead. Molecules take the shape they do, combining states of the quantum rules. Like when a shell goes sp2 for sigma pi double bonding. And as widely as their purview, they spread it in the molecule. Look at benzene in a ring, they hold it true, aromatically bonding. Low, high, low, high, low, high, low, high. Aromatically bonding. Low, high, low, high, low, high, low, high. Aromatically bonding. Low, high, low, high, low, high, low, high. Aromatically bonding. Look at benzene in a ring, they hold it true. When orbitals take the shape they do. Come bond with me, baby, come bond. 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 Polymers take the shape they do, combining base level residues like RNAs, ACGU, with their hydrogen bonding. Peptides make a chain and group, and beta plate sheets and corkscrews. With the secondary links they fold and move. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. Come bond with me, baby, come bond. Come bond with me. They're all over your body. You're a chemical machine, it's best you knew. The molecules take the shape of you.
Okay, so I hope now all of you have got clear what are all these particular spin, what are all this particular property, and how we are getting those shape. Okay, so it's like every atom will going to arrange in their own fashion with those particular quantum spin and electronic state, and further in the superposition they will going to behave as a single particle. And the latest example, all of you aware of it, like it's a very common example where people are trying to explain the quantum theory using the Heisenberg's uncertainty principle. Okay, so where they have shown a cat in a box. So definitely this particular thing is nothing but what, when we are having a particular cat in a box means what, a particular atom in a box, and then at that time we're going to think what that particular atom will going to do. So when we are considering a cat in a box, So that cat, either it will be alive or it will be dead when we are considering the classical mechanics. But when we are considering the quantum mechanics, it's not necessary it will be alive or dead. Okay, so it may be in the both state at the same time. Okay, or maybe there will be the another state where cat may dance, cat may going to say hello, okay, with her palm in your hand. Okay, so like that, there are different probabilities which through which we can able to explain what that particular cat will going to do. So this is what the quantum phenomena is, nothing but what the different thing which you are considering. So it will not going to behave as a classical mechanics. So definitely when we are talking about the quantum, so it always comes into picture computing. Okay, so most of like all of you have heard about the quantum computing. Okay, but now like India has launched NQM, National Quantum Mission. So through that we can able to get the all different quantum devices and different fields also. But previously when NQM was not launched, but people have restarted their work in computing. So there are two types of computing as we know, like classical computing and quantum computing. Similarly, there are different types of physics chemistry also, like bio also, it's a classical physics, classical chemistry, and the quantum physics and quantum chemistry. So the both thing which can easily understand, like in classical computing, the bits, okay, or the storage which we will going to do, either it will be a 0 state or it's in a 1 state. Where in quantum computing, we will not going to sure either it will be in 0 or it will be in 1. It may be superposition of 0 and 1 as per the probability of those particular conditions. Then the second is no data restriction to create a copy of arbitrary state. Okay, so we can easily create the arbitrary state in the classical computing, whereas quantum computing, as it's based on probability, so it's a restriction always for creating those particular data or arbitrary state. The classical computer have less compute power, whereas quantum computers will going to require higher power. Classical programs will going to produce the result as per the given input, whereas quantum computer, they are always probabilistic. Like we are saying, like 1 plus 1 is equal to 2. Okay, whereas in quantum computer, it's not always like 1 plus 1 is equal to 2. It depends on what's the probabilities. Then according to the maximum probability where it has assigned, that will be your final answer. And in classical computing, we always say those particular data store in terms of bits, whereas in quantum computing, these particular bits are called it as qubits. Bits are independent, like they are independent of each other. Okay, like for example, there is one MOSFET and nearby second MOSFET, the nearby third MOSFET, and the one MOSFET is on, another MOSFET will be off. So their on and off will not going to change in bit like their own state. Okay, so one is 0, like one MOSFET is 0, second MOSFET is 1, then definitely they will remain as 0 and 1 until and unless we'll give a certain input to change it. Whereas in case of quantum computing, the bits are dependent. Okay, so the nearby bits are always changed by their neighboring behavior. So the whole thing we can say, like those particular qubits will going to change or they are always dependent on their interconnection, and always depends on the periphery where they are uh, uh, storing or staying there. Okay, and the last is classical computing is a one state at an instant. Okay, so we can always get a one state at a single instant, whereas in quantum computing we can able to derive, or we can able to compute, or we can able to solve multiple state at a single instant. So like in a one instant means what, like we are using a particular adder or subtractor or something, and then we are going to add those particular bits and we're getting that particular answer. Whereas in case of quantum computing, we have a probability of those particular inputs, and then according to those particular circuit we can solve the multiple probability equations at a single instant. Okay, so here this is what the representation of the bits, like 0 and 1, only the two bits will be there. So 1 is there, then 0 will be of 0%. Okay, so whereas in case of quantum computing, these bits are called it as qubits, or we can call it as block sphere, and this sphere consists of like upper side we can consider it as 0, for example, and the downside we are considering it as a 1. Okay, and then probability of it will going to say what the qubit state is. Okay, So this is what a single block sphere, and or we can say a qubit. So it's a 0 and 1 state, and this is what the where the arrow is notating. So we can say this is what a single probability state. Okay, so from here we can say the 50% is 0 and 50% is 1. Okay, that we can say. Whereas in this case, so there is a probability 0 and 1, those will be the 50%. Okay, so if it's pointing upward, so probability of 1 will be 100 and the 0 will be 0. Okay, sorry, probability of 0 will be 100 and 1 will be 0, and the vice versa. Okay, but when we are putting this particular qubits in the nearby area, like if you're having a memory device, we are storing the 010101, so like that we can able to store those particular data set in this our qubit structures. Okay, or we can process that particular set, like we are processing in a processor, same way we can able to process the data using qubits. So when we are having two qubits in the neighboring, so it's not necessary like in a classical computing, we can say this particular thing is 0 and this is 1, and they will not going to interfere each other data. Whereas in qubits, they will always interfere each other's data. Okay, so this is what the first bit, which is of 30% 1 and 70% 0. Second bit is 40% 0, 60% 1. Okay, so these both bits will going to interfere each other, and they will give a certain kind of a probability, like these are what the different state which we can achieve using these two bits. Okay, so normally when you're considering two bits, so either it will be, so there are possibility of 4 state only. So it will be 0 0 0 1 1 0 and 1 1, but all those 4 state will going to have a probability in quantum computing. So for example, 0 0 it has 5%, then 0 1 45, 1 0 12, and then 1 1 will be 13. Okay, so these number of state we can easily say like these are what the number of bits. So those many number of state we can able to identify using this those number of qubits. So why it's happening? So when we are considering a block sphere or a qubit, so that particular block sphere is always represented by a certain wave function. So this wave function comes into the picture in the Schrodinger equation. So that particular equation has a probability of those particular particles or the electrons, how it's behaving, okay, and at what state it is there. So that particular qubit has this particular wave function. Similarly, other qubits will going to have a different function. So when they are superposition, okay, so this is what the superposition means. They will going to interfere with each other, and they will produce one single function of all those particular bits. So these are what the number of bits which you are getting, and the probability of those particular state will be easily getting from it. So we can easily say like when a water drop is falling into an ocean or into a stable water, so it's like a kind of, it's going to interfere with the nearby atoms also. Okay, so like that in the classical computer, we can say the drop particular is coming, so it will just drop there and it will stop. Okay, whereas in the quantum, so that if that particular drop is coming, so it will going to interfere with the neighboring atoms also. Okay, so we can easily understand this thing using this particular example. Like a certain wave function is coming and it will going to interfere and it will generate another kind of wave, okay, which has a different probability which we were expecting in the previous state. Okay, so I hope it's clear, like nearby qubits will interfere with each other and they will give a total output, okay, as a probability of those particular states. So why it's necessary to have those particular probability theory and how it will going to help us? So the simplest example, as we all know, in quantum computing, when we are, so quantum computing, we always say it always, so it will be always used for an application for encryption or decryption, like securing the data, right? So this securation of the data, so it always secured through the factorization method. Like for a number, we have given as a password or something for our bank account. So the algorithm which is there at the bank level, so those particular algorithm have assigned a certain password to each and everyone's account. So those numbers which are there, so those are very complicated and bigger number. So it's very difficult for us to factorize those number. Okay. So whereas in case of like when we are considering the classical computing or classical computers, so they will take longer time to solve those particular factorization. So it's like when we are given 4 as a number and we ask us to factorize that particular number. So what we'll do, we'll just check what is so it will be multiplied by divide by what. So we will say it will be divided by 2. Okay, then again 2 will be divided by 2. So finally will be 1. So we can say 4 written as a factor of 2 into 2 into 1. Okay. Similarly, if there is a bigger number, so it's very difficult for a normal classical computer to solve it. Okay, so it will going to follow the step by step or the sequential order, and those particular number of state will require. So we can say the number of digits. Okay, how many? So 2 raised to number of digits steps will going to follow for solving that particular factorization. Whereas in case of quantum algorithm, so we can able to solve the same thing just with the log of n. Okay, so it's like we are solving with the 2 raised to n number of steps, or we're just solving log of 2 raised to n number of steps. So we can say it's a very few steps will be required when we are using quantum algorithm for solving the same factorization. So the simplest example for quantum computing is the Shor's algorithm, which is well known and the first very well and famous algorithm. So it explains the same thing, like we are factorizing a number, so it will say 2 raised to n, and we're going to use just log of n, and we'll be getting those particular equation will be solved in a few, like only just one step or 2 steps. Okay, so like that, this quantum computing will help us. So this probability only will going to help us to solve all those particular expressions in a few instant. Okay, so how, as we have seen already a difference, like in a classical computers, it can able to solve a single step at a single instant, whereas in quantum computers we can able to solve the number of state at a single instant. Okay, so that's a parallelly we will going to execute those particular factorization, and we will easily get out the factors of that particular number. Okay, so it's a kind of very good for us, so that we can make our account more secure, but as well as it's hazardous also. If someone got the quantum computer or quantum algorithm first, so it may possible the hackers can easily crack our security code, and they can easily damage our like security of nation, and as well as our own account security also. Okay, so who are these 3 people? Okay, as we have seen, like, and also we have seen the video also. So what we have seen, like those are the smaller particles will going to show the quantum nature, but these 3 people, okay, they have already demonstrated in 1980 like quantum behavior we can observe at macro level also. Okay, so they used superconductors, and there is a smaller gap of a higher potential, and they have checked like a electron which is traveling into, or we cannot say electron, we can say a charge carrying particle which is moving from one end of a superconductor, and there is a whole potential gap, and the another superconductor is on the other end. So that particular charge particle can able to travel into the next conducting superconductor, which is separated from the first superconductor by a very huge large potential well. Okay, so if there is a potential well, then how that particular electron has traveled? Okay, if there is a well, so electron must going to collide, and it will not going to travel at the other side if you're considering electron as a particle, because there is no way that particular electron will going to interact with that particular well and then travel into the next superconductor. So from this particular example they are shown, it's not just electron, okay, or the electrons will just behave in the smaller quantum dots, or the or the we can say quantum particles. Okay, so it will not going to behave as a quantum particle at the nanoscale. Okay, it is possible that particular quantum behavior, or the we can say a wave or particle and then particle behavior we can observe at the macro level also. Okay, so they got Nobel Prize in last year only, 2025. Nobel Prize has given to this famous scientist. Okay, so they have demonstrated in 1980 only, like we observe quantum phenomena, okay, at the macro level also. Okay, it's not just only at the nano level. Okay, so what is quantum computing? So it's so there are two types of quantum computing we can able to observe. Either it will be adiabatic quantum computing, where minimum energy level and optimize, we can able to optimize it accordingly, or topological quantum computing, where we can use a quasi particle, and those particle state we can able to use for solving this quantum computing. Okay, so using those particular computing, so who are these two people? Okay, so they got the Nobel Prize again. So these are the two people who has find out or help us all to get the vaccine for uh, coronavirus. Okay, so pandemic which we have seen in the 2020, and that particular pandemic where we got the vaccine also, but still it required 1 year for the reproducing like those particular vaccine, but they have already developed one and it will going to give another sequence of an RNA through which we can able to say like this is what the virus sequence. Okay, and then this will be our vaccine sequence. Okay, so like that we can able to give a antibody, okay, or an antigen for that particular virus, and we can insert into our own body. So this simulation, okay, it's required use server to solve those particular RNA states. Okay, but if we have this quantum computing computer, which they required 1 year for getting that particular sequence, it may like we can easily get it in the within few months. Okay, so normally this particular quantum computers, or we can say quantum computing, we can easily get it through this particular characteristics. So either we can have a material property and we're going to add one certain elements, or we'll just pass on through it and it will going to change its state, and that state we can observe. Okay, and that state will consider it as a change in a state, and we can say it's a information for that particular bit. Okay, or we can have a certain chemicals which they will going to react and they will give a certain product, so which we'll consider it as a another state. Okay, so this is what the simplest qubit model which we have already seen, like it's a adiabatic computing and topological computing. These two computing we can have also. Okay, so in the qubit model, so this two topology we can easily able to get it from this. Okay, so we can say all these are the different qubits which are arranged in a array fashion. Okay, it's same as the bits which we are storing, or which we can see in the classical computers. Okay, it's like every MOSFET has a certain state, so that will be a 0 or 1 state. Similarly, we can have those particular qubits. Okay, 1, 2, 3. So those many quantum qubits or block sphere which we have, and they have a certain probability function. Okay, and this model which we can use for computing the our algorithms. Okay, so nowadays we already have algorithm, but we don't have quantum computers through which we can able to run those particular algorithm. So for example, this is what first bit, second bit, third bit. Okay, so every bit we can able to track. Okay, so there will be a certain sensor through which we can able to see like what this particular bit is what. Okay, and from that we can get the probability. Okay, so every bit has a certain function, and that function we can easily capture, and then we can process further using this particular certain gates which we'll be using, and we are passing on that information to these qubits. Okay, so that particular qubit will change its state, and that data is stored on this particular in the this particular qubit. So this is what a simplest example, like this is what your whole array. This whole array we can able to change its state according to the what information we are passing into the qubits, and what information will be like we can able to observe at this particular state. Okay, so it's easy for us because we know what's the function which we have used. If someone is trying to crack this particular qubit model, so it will be difficult for him. Why? Because he can observe all these different state at a single instant. Okay, so there is a probability of the different states which we can able to observe. For example, as we can see, it's a 101 state at the final, but when we don't know what's algorithm is there, so we can able to see all the states with the different instant. Okay, at the same instant, what are the different states? For example, it's like if there is a 000 state, that much percentage is there of probability of finding that state. Then 010, so probability of finding that is this much. Okay, so like that we are getting the probability of those particular states. But if we know the function which we are applying and we are storing the data into it, so it's easy for us to find out this is what the probability of that state, and it's the highest state, and that we need it as a data. Okay, so as per the algorithms we can easily develop, and those algorithms further we can use a certain things to store the data. Okay, so what are those things, how we can store data in a qubit? Okay, so that we can easily see in the further slides. So as we have to know what are the quantum algorithm and that, so definitely we must know what's the quantum computing roadmap. Okay, so this is a roadmap given by IBM. So by 2030, so they are expecting, okay, IBM will be capable of having their own quantum computer, and they can able to solve all the quantum algorithm by the end of 2030. Whereas in 2023, they have strategy like they can able to develop the they will going to introduce the quantum window. Okay, and then we can able to have the different algorithm through which we can able to solve it. They have also provided server to the users or to the university, where researchers and scientists they can able to develop new algorithms in the quantum era. Then in 2024 they expanded the same thing, okay, to all over the world, where people can able to develop more algorithms, as well as there are okay there are certain quantum circuits which will be allowed for those particular users. Okay, but they will charge only a few dollars fees for using those particular quantum circuits. Okay, so what are the algorithm which they have developed, and then further they can process it through those particular quantum circuits and quantum devices. So that particular circuits which they are using, so they will definitely give or built in a certain error. So it's like a new device which we have developed, and definitely we're going to test it. After testing it, it will give a certain error. So they are like, it's like a probability of finding the number of state. Okay, and then we'll go to check whether that particular device is working or not, whether it's accurate for that particular algorithm or not. Okay, so like that they are observing which device or which quantum device will going to work further for those particular algorithms. Then in 2025, okay, so it's like a demonstration of quantum centric supercomputing. Okay, so it's like the number of gates which way they have provided previously is like 5,000 gates. Now it's modular to allow running around the 7,500 gates at a single instant, which we can solve our algorithm which they provide us to use it. Then all these particular circuits and those things which we can use, and we can see whether we can able to solve our algorithm or not. So it's like the system is there, trial and error, solve it. Then in next era, we're going to give the more sensors or more qubits, and then again solve it. Okay, so like that they are scaling up further, and then finally at the 2030 we'll be getting our final quantum, or we can say a supercomputer, which again a quantum centric. Okay, so nowadays we have supercomputer, but which is not quantum centric, which is around the classical computers only. Okay, but If you have a supercomputers, which is quantum centric, so we can imagine like quantum qubits, they have a probability function. They can solve the key of any like cryptography, that thing in a few instant. Okay, if you have a supercomputer with quantum add-on to it, so it will going to solve those particular thing in just only a few instant. Okay, so so by 2030 IBM is planning, okay, to have their own supercomputer with which is around like which also help for the quantum centric. And definitely you must be thinking like whether it will going to the way which we got the previous phones. Okay, now those particular Nokia 100 now we can't see, but nowadays everyone has a smartphone. So whether is it the same thing that quantum computer will going to replace our classical computers also? Okay, but it's not. Okay, because classical computers, they can easily used for multiplication purpose. Okay, as per the multiplication is always works on MOSFET switching. Okay, ultimately what we are storing, it's always a MOSFET switching 0101. When you're doing a multiplication on a classical computers, so it's easy for us to get the accurate result. But whereas in case of quantum computer, if you're doing multiplication, so it's very difficult for us to get the accurate answer because it works on probability. So all those probability function of those particular number. Okay, so now you can imagine we are multiplying 10 by 10, it just 100. It can give us the answer in a few steps using the classical computers. Whereas in case of quantum computer, it will give in a few instants, but the thing is the energy which is required for solving this particular issue, it's a huge amount. So rather than going for the quantum computer, so we can use those particular multiplication, or the simplest thing, we can use it for the classical computer. So definitely we can say that in future, we can observe classical computer and quantum computer, they will go hand in hand. Okay, and like that, they will going to evolve our humanity around the globe. So this is what the simplest example where we can see like when you're considering the VLSI, then how this particular quantum will help, okay, us to develop the or integrate it with the VLSI. Definitely we know what the MOSFET limitations are. When we are moving as per the Moore's law, when we are moving towards the smaller and smaller size, so there are limitation which is due to the leakage current. So that leakage current is nothing but we are shortening the channel length. Okay, and that particular channel length, so definitely we are also shortening the thickness of oxide. Okay, so the electrons which are attracting or which are helping us to form a channel, it's not necessary it will going to enter like it will going to be there at the channel region. It may possible as the channel length is low and the supply which are applying to the drain and source, it may be possible that electron, as it's going into the smaller and smaller size, which is in nanometer, that electron will not going to act as a particle furthermore. It will act as a wave, tunnel through the channel, which is as an insulator, okay, and then enter into the drain region. So like that, we are getting a certain current. Okay, so that particular current we called it as leakage current. So this leakage current we are getting because of the electron the dual nature. It's like it acting as a particle, but when you are moving towards the smaller size, it acting as a wave. Okay, so there are, so this particular limitation are further over, like we have a planar design MOSFET, then FinFET, okay, then it's like a rounded gate FET. Okay, so like that we are getting this particular different structure so that we can able to solve the leakage current issue. But as per the Moore's law, we are saying after every 18 months, the number of transistors which are there in that particular area will get double. Okay, so to follow the Moore's law, so definitely we must think or we need to proceed further a certain new or a certain new era where we can able to overcome all this particular issue related to the MOSFETs. Okay, so that particular era we can able to go and check and we can able to find out using the next designing of the MOSFET. Okay, so these are what the simplest pictorial form of the MOSFET. Okay, so round gate and the GA gate. Okay, so those are we have seen. This is what the evolution of FET. This is what the normal FET was. Further FinFET, then stack nanosheet FET. Okay, then gate dielectric FET. So all these different gates, the different structures are developed just to overcome this, and we can able to still follow the Moore's law. Okay, but this is what the leakage issue. As you can see, this is what the electrons, which is tunneling on the other side. So is it possible to use this particular electron behavior as a advantage? Okay. Yeah, so it is possible. So Dr. Suman Gupta has demonstrated where he has used this electron tunneling as a switching. Okay, so when electron is moving from here to here, so it's considered as a 1. Okay, bit 1. So he has developed a particular MOSFET where he has used gallium arsenide as a substrate, and the through which we can able to see, like, this is what the structure of a MOSFET, this is what our source, and this is drain channel region. Okay, and the electron. Okay, so this particular thing we can consider it as a wider gap, or we can say it's a huge energy gap, or we can say a huge potential difference is there. So the electron which is coming from source, okay, it will not able to enter into the channel, okay, because this particular potential window is huge. Then what he observed, when we are reducing the channel size to the very smaller scale, okay, which is in nanometer, so this electron, which was not passing at the macro scale, but it can able to observe, okay, on the other side when it goes into the nanometer scale. Okay, so this particular scale here, you can observe it's around the 50 nanometer, and this nanometer scale we can able to see, like, this is what the structure of our MOSFET which he has observed, and this transistor they called it as tunnel transistor. Okay, so instead of using like those particular tunneling of electron, which is a disadvantage in the normal MOSFET, so we can using that the same property as a advantage for us, and we can create a tunneling MOSFET in the future. Okay, so definitely we can do research and further move into, like, is it possible to have this kind of MOSFET where switching on and off will not be controlled by the electron traveling as a particle. So it can be used when electron is tunneling into the MOSFET. Okay, so this tunneling will going to help us to switch the MOSFET at very low potential. So normally when there is a huge potential barrier, so we need to give a huge potential to the source, in between the source and drain, then and then only channel will form, and at the gate we have to give the potential also, and the channel will form and the electron will going to travel. Whereas in this particular tunneling transistor, there is no requirement of that much huge potential. We just give a few millivolts and the electron will so there is a huge potential barrier. Just few millivolt is enough for making that electron to jump or make itself convert into wave and appear at the other end as a particle again. Okay, so as we have this particular quantum tunneling MOSFET also, so it's possible for us to build a quantum computer also. So you must be thinking, as we are using electron as a wave, so there are so many waves in the nature or in the periphery which may interfere with this particular quantum computer. Okay, so that's why you must have observed in the series or in movie on the or in the picture, you can see whole thing is like a bigger thing which is of a quantum chip. It's made up of gold and many wires are there. Okay, but actual quantum processor is very small, but all those periphery which they have used, they used it for protecting that particular quantum processor. Okay, so these are what the different things which will interfere with that particular quantum processor. So it may be a cosmic rays, which are electromagnetic waves which are already present in the environment. It may be heat, okay, which may change the quantum state, and it may be the other radiation which is coming from us or from the other hot body, or it may be the particles which are present in there at that particular atmosphere. Okay, so all these are the possibility which may interfere with the quantum processor where we are trying to process our data. Okay, so there they will going to introduce a certain error in our processing data. So to avoid that, so there will be we can say it's a new research field which we need, through which we can able to develop a certain casing. Okay, so that particular casing can able to handle all these interference. Okay, so it will not going to allow any cosmic ray to enter into that. Okay, it will also maintain the temperature. There will be no particle will going to enter. There will be no radiation which will going to enter through that particular casing. Okay, so we must be thinking of there we need a certain packaging. Okay, that packaging will help us to overcome all these problems. Okay, so like normal ICs, they have a certain packaging. So that packaging also designed in a such a way that there will be no any other environmental impact on the IC. Okay, there will be the good heat dissipation into the environment from the IC. Okay, so like that, the packaging has designed for the normal processor. Whereas for quantum also, there is nothing, but now we have to evolve and we have to do research for this kind of packaging for our quantum processor also. So all those particular gold thing which we observe, so the gold thing are nothing but what this. Okay, just to avoid or protect our processor, quantum processor, from all this particular noise. Okay, so those gold things has introduced. Okay, so regulating the temperature, avoiding from the any radiation, avoided from any interference of the cosmic rays. Okay, so this particular super quantum computer, they can develop using the different we can say phenomena or the different storing mechanism. Okay, so the first storing mechanism, it's using the superconductor. Okay, so as all of you know, what's the superconductor? Like we know what is semiconductor, we know what is conductor, and we know what is uh, insulator. Okay, but whereas what is superconductor? Superconductor is nothing but what? It's a conductor, but it has zero resistance. Okay, so the electrons which are traveling in the conductor, they will collide with the phonons of that particular conductor. Okay, so phonons means what? If you're considering a copper, now copper has a certain lattice structure. They has in atoms are there arranged in its own fashion. Okay, so now those particular atoms are oscillating around their mean position. Okay, as you are considering electron as a wave, so definitely electron will going to oscillate at around its mean position in a certain fashion. As electrons are oscillating, so we can say the whole atom is oscillating. So that atom oscillation has also a certain wave function. Okay, so every atom will going to oscillate at their mean position. So now when we are considering that copper as copper as a conductor, so when we are supplying a certain potential, means we are giving electrons to the copper. Now that electron will travel into the copper and towards the other end. But it may be possible that electron may collide with the atom, okay, which is moving around its mean position. Okay, so it's not necessary like this is what atom is moving, and electron will come, it will jump, and it will go. Okay, it's not. So electron will come, okay, it will collide, and it will lose its energy. Okay, that's what we call it as resistance of that particular conductor. Okay, but whereas in case of superconductor, the superconductor is always first thing is always at the very low temperature. At very low temperature, the atoms will not move around their mean position. So, okay, so the phonons will not be there. Means atom will be stable. And the next thing is, as the atom is stable, means what? Electron will be stable. So the potential which we are supplying to it, so that superconductor will develop a certain thing, which we called it as Cooper pair. So Cooper pair is nothing but a positive and negative charge put together, and they will just travel along the superconducting material. Okay, so they will not going to collide with any phonons. Okay, because these atoms are stable, they will be fixed at their position, and there will be a gap in between the atoms, and that gap will be used as a road for that particular charge carrying particle, which you called it as Cooper pair. So it will just travel in a short. So that's how the superconductor is a zero resistance material. Okay, so now this superconductor behave differently when we are applying a magnetic field across it. As I was saying, superconductor will not going to have any resistance, but it may possible the magnetic field may change its resistance. So that's how we can able to use the magnetic flux, okay, for storing those particular states in a computer. So if you are using the superconductor as a storing material, then we can use a magnetic flux, okay, and what magnetic flux which we are giving to that particular superconducting material, that's what the thing which is there. Okay, so the magnetic flux is proportional to the what information we're storing into that superconductor. Okay, so that's how the one mechanism through which we can able to store the information in the superconductor based quantum computer. Okay, the next computer which we can develop, or the next chip which we can develop, it will be through the quantum dot. So the quantum dots are all of you aware. So mostly the all the semiconductor which we observe nowadays at the macro scale, the material like silicon, germanium arsenide, and their different composition. So all those materials are the semiconductor in nature. But the same material which are moving into the smaller side with the nano size. Okay, so but how much nano size? So that nano size is nothing but what Bohr radius of that particular compound. Okay, for example, we are considering silicon. Silicon has a certain Bohr radius, and we are synthesizing a silicon quantum dot or quantum sheet, okay, or quantum rod. So that silicon quantum sheet or quantum dot has same size as our silicon Bohr radius. If the size of this particular silicon nanoparticle is comparable with the Bohr radius of silicon, so that silicon will not going to act as a certain nanoparticle. So it will enter into the quantum state. In normal nanoparticle, that particular electrons will behave as a particle. Whereas when I'm considering a quantum, so that electron will behave as wave also. So like that, we can able to synthesize silicon-based quantum dot or germanium arsenide-based quantum dot or diamond-based, means what? Carbon-based quantum dot or graphene quantum dot. Those particular quantum dots we further use for storing the our information. Okay, so that particular information we can store using either voltage, magnetic, or microwave. Okay, these are what the different source through which we can able to store our data. For example, like in normal MOSFET, will give a certain gate potential and it will store like 0 or 1. Whereas in case of quantum dot, we can give voltage or we can use magnetic field also. Okay, so for around this, so what these are the yellow color are nothing but the electrodes, and in between, so it's like interdigital electrodes. Okay, like this. Okay, and in between these digited electrodes, we are putting a quantum dot in these particular slots. Okay, so now what potential we're applying, that will going to attract those particular quantum dot towards the one side, and that's how we have changed the quantum state of it. Okay, so we're applying a certain potential, the electron will it will going to form a dipole. Okay, and that's how we have stored the quantum information in that particular device. So this is what the another computer which we can develop using the quantum dot. So we can call it as quantum dot based quantum computer. Then the next is commonly most we have, as we had already seen, quanta, okay, and the photons. Okay, so everything comes from the Albert Einstein. Okay, so that particular photon we can use, okay, in developing the optical quantum computer. So where we can able to develop certain quantum devices, we can able where those can able to generate a single photon. Okay, a single photon. Normally the source which we are getting, it produces the millions and billions of photons. Okay, even laser packets also, even just a single opening of a shutter, it will give a number of or bunch of photons. So what we need for optical quantum computer, we need a single photon generator and as well as a single photon detectors. So those single photon generator and single photon detectors which we can use, okay, which we can use, and that particular photons will going to travel, and that's how we can get the information or store the information. So either we can use a mirror, waveplate, or interferometer as a storing mechanism. Okay, for example, a single photon which is generated is of red color, and here is the detector which is detecting the single photon of red color. Okay. Now the next thing, if you want to store information, so we can add a wave plate, okay, or we can add an interferometer where two photons can interfere and they can give a different kind of photons, okay, which will be not detected. So we can consider it as a certain state, okay, or we can say a certain mixing of color. It has a certain kind of probability of this much red and this much green, and like that we can able to say like this is whatever quantum information which is stored in the device. And the same we can use it for, like, for example, like if you want to add something or subtract something, so those particular different photons we can pass through the interferometer and it will generate another kind of photon, and that photon we can detect and it will be given as output. Okay, so like that we can able to develop a optical quantum computer. Then the next quantum computer which we can develop is through the trapped ion quantum computer. Okay, so they will be using a single ion and that will be trapped in a certain potential value. So here you can see these are the 4 electrodes. Okay, though, and this is what is the cavity where the particular ions has trapped. Now we are applying a certain potential to those electrodes, so that ion will going to shift. Okay, so either this ion is positive, so it will little bit shift towards the negative charge. So that shifting will decide what kind of information is stored. Okay, so that's the one thing. Another thing, we can easily shift that particular ion using laser or using microwave. Okay, so we can give a certain kind of a single, like a laser. It will going to excite that particular ion, so it will not going to remain as that particular state. It will be in an excited state and it will remain in that particular state. Still we retract the information from it because it's a trapped cavity. Okay, so that particular ion will remain at that particular state when we are giving outside energy source to the atom, and it will be at higher level and it will remain at that particular state as it is. So like that we can able to develop the trap ion computers. Then the final is our color quantum computers. Okay, it's the simplest and very easiest one. So it's easy for us to synthesize all these quantum dots at the nanoscale. For example, we can easily synthesize. This is what the image you can see. This is a graphene sheet. Okay, so it's a planar graphene sheet, or we can call it as a quantum sheet, which is doped with the nitrogen. Okay, because we have synthesized in that particular using that particular chemicals. So where this graphene has nitrogen atoms also. So this graphene, which is like acting as a electron clouds are there. So when we are adding nitrogen to it, so it will change its doping. So for example, when you're having a normal graphene quantum material, so it will be always excited in the UV light. Whereas if you're adding a nitrogen as a dopant or as a impurity to the same atom, it will change its excitement, the excitement or excited wavelength. Okay, so for example, if it's instead of UV, it may possible it will excite at the visible region also, or it may excite at the another different wavelength also. Okay, so that particular source we can use it as a information writer. Okay, so this particular quantum dot is stored in one cavity, and we'll just, where we want to store the information, we'll just shine the laser on that quantum dot and the information will be stored. Okay, so like that we can able to switch it to the different 0 and 1 thing. Okay, and the last is your
Pranav, sorry to interrupt you. How many slides are remaining?
Last, sorry, this is last.
Okay, because we have to go for test. Okay.
Yeah. I got it. Only 3 minutes.
We have to log in. Okay, thank you.
Okay, so the last is your neutral atom, where we have atoms are stored at the freezing state. Okay, and through laser we can able to write what information we need into this or store into this particular neutral atom based quantum computer. Okay, and so that's how we have completed the quantum session. So we have almost gone from the classical physics to quantum physics. Okay, classical MOSFET to quantum MOSFET, and then classical behavior of the bits to the qubits. Okay, so like that we have covered almost everything. like we have developed, like we have covered classical everything as well as quantum everything. So it's like an overview of it. And if you want to learn or learn about the quantum computing and these things, so you can easily log into QSkit of IBM, and where you can able to develop your own quantum algorithm or continue your quantum based research. Yeah? Okay. Thank you for this, and also thanks to my professor Dr. Nita Doshi and Dr. Yuvraj Polkare for giving me this opportunity for presenting the quantum horizon or the quantum knowledge which I know to the such a wonderful audience. Yeah, so anyone has question?
Participants are requested to ask the questions, or you can post the questions in chat box also. Okay, so because we have to go for quiz at 6:30. Okay, so we have only 10 minutes. During this, we try to take few questions.
Yeah, any question related to qubit or sensors or any fabrication related thing you can ask.
Okay, meanwhile, I have a question.
Yes, sir.
What are different job roles that can be created by quantum computers, and what kind of skills that should be pursued by maybe faculty or researchers?
Yeah, definitely. Okay, so in quantum, like National Quantum Mission has just now launched. Okay, so where we can observe all those different four field. So if you want to work in a quantum computing, okay, so definitely we can use this particular platform of IBM, through which we can able to develop our own skill. So they have their free lectures also are available. How to start with the quantum computing from the basic, and how we will going to advance to the advanced level also. Okay, and the next thing, if as someone is working on the fabrication or in the VLSI domain, so definitely instead of like we are designing a particular MOSFET, so we can able to develop a certain MOSFET, okay, where we can able to have a gate which is made up of quantum material. Okay, so where we can put instead of a gate material, we can change it to a quantum material, and like that we can use the tunneling effect also for storing the information for the fabrication. Then in case of sensor, we can develop those particular quantum particle based sensor, which we can coat it on a sensor, like we have sugar detection and that. So similarly, we have a 2 electrode or 3 electrode system where we can coat our quantum dot, and we can able to get the real or the accurate information from it. Okay, for example, nowadays the diabetes has a huge window. This is what the sugar level has to be there in the human body, but we don't know what's the actual thing. Even though some person they're having a lower sugar, still they are active. Some person are having the higher sugar level, still they are active. But what was the real level? Okay, so those accuracy we can easily maintain it through the quantum material. So definitely we must have a fabrication knowledge also, which we can able to get it through the fabrication facility which are there either in a CMET or in Semiconductor Bombay or in the ICER Pune. Okay, and also ICER Pune is our the IQ hub. They give a certain courses which are related to the quantum. So those are related to the quantum computing as well as the quantum devices also. Okay, by doing those particular summer internship for students or faculty development like program for faculties, and then we can able to get the knowledge from those particular courses also.
Okay, thank
Yeah,
you.
so
Thank you for your explanation.
Yeah. So it's time to give vote of thanks. Parkai sir, shall I proceed?
Yes, yes, ma'am. Yes, ma'am. Proceed.
Oh, okay. Because the time 6:30 is there, so we have to rush. Otherwise, we really wanted to listen to Dr. Pranav, right? Okay. So to extend our sincere gratitude to Dr. Pranav Pawar, our esteemed guest of honor, for today's ATAL Faculty Development Program, his rare interdisciplinary perspective seamlessly connecting electronics, material science, and emerging quantum technologies added exceptional date to the session. His research expertise spanning nanomaterials, graphene based devices, energy storage, water purification, flexible electronics, and quantum dot-based sensor technologies, was truly enlightening, Pranav. The relevance of this work on quantum dots and low dimensional nanomaterials to next generation quantum devices, sensors, and nanoelectronic systems made the session both timely and impactful. So, on behalf of the organizing team, I thank Dr. Pranav for his insightful talk on introduction to quantum devices and exploring the horizons of quantum, and for inspiring us to explore the future of quantum science. So, hats off again to our alumni. Pranav, thank you for giving us a time and an opportunity to get the knowledge which you have gained, because being in academics we are really unfortunate to get touch into the industry, but then this faculty I know was a bridging gap between academics and the industry experts, and with your expertise you truly, like, it was really a good, very good end session where everyone enjoyed it, and you see in the comments you have all the comments and all that. So thank you once again. I had a call. I'm so sorry for that. But then really, we will be in touch, and I'm sure all of the participants, the faculty members, really enjoyed this session. So thank you once again, and over to you, Parkare sir. Are you there?
Yes, ma'am. Yes.
Yeah, for the exam, right? We have to go.
Okay.
Thank you so much, and all the best to all participants for exam.
Yeah, that's really, because all the participants, these questions are framed by the speakers directly. The esteemed speakers have framed the questions. So really, all the best for everyone. Over to you, sir.
Okay, thank you, ma'am. Now participants are requested to log in into their ATAL portal. Okay, at 6:30 the link will be open automatically. We have scheduled from 6:30 to 7:30. Okay. I think we wait for 5 minutes. After the test, every participant has to fill the feedback form in a ATAL portal itself also. Okay, I have given overall attendance form also, that is Google form. Okay, but you have to complete your exam, and then you have to fill the feedback form in your ATAL portal. Only then your marks are visible. So wishing all the best to all the participants for the test. After the test, we have a feedback session and validity function from 7:30 to 8. So all the participants are requested to give their feedback for 1 minute, 2 minutes. Okay. And also attend the validity function. Okay. So thank you and all the best.
Sir, are you able to read the questions in the chat box? They are asking, do we need to log into Zoom again, or should we continue with the live session?
You can continue the live session, and you can log in into your portal. If you have any query, you can ask online.
Yeah, so just open the chat and keep, because after 2 minutes you will be sharing the ATAL link, right?
No. Actually, link is that is from their own login.
Okay.
It is already active. Okay.
Oh, see, instructions to all the participants through your login. The link is already active. You can join that. You can remain connected in this.
Just go to your ATAL login and then there is a tab called test. Okay, open it. It will get active.
All the participants, if you are able to hear, Porkare sir is instructing you all, please. Sir, can you please repeat?
The procedure is very simple. Go to your ATAL login first, then go to your test tab. Okay, so it will be get active at 6:30.
Go to ATAL login. Then what they have to do, sir?
Then they have to go for test tab. There are FDPs, test tab. Okay.
FDP test tab.
There is a time again, 2 minutes are there. It will get
So
active.
we could have continued with Pranav, sir. The session was really so interesting.
Sir, there is
Yeah,
no
but then all
tab
the
for test.
participants.
Sir, there is only test marks tab is there, sir. Test marks.
Okay.
No test tab is there, sir.
Ma'am, there is a assessment tab. I don't have the participant, so one of the participants has shared. Go to the assessment tab.
Yes, sir. I am able to
Yes,
see
sir.
assessment tab.
Yes,
Okay.
there is a
And there is one link is I have seen 19,126. Yes, sir. Okay.
Yes, sir, you can join.
Thank you, sir. Thank you.
Sir, can we start from that link?
Yes, yes. At
Yes, sir. Yes, sir. If
6:30. Yes, if it is
it is
active, you can
visible, you
start.
can start. No problem.
Yes, sir, it is visible, sir.
Okay, sir.
Then
You can
sure,
start,
sure.
no
All the
problem.
best, all the participants.
It's for 1
Thank
hour.
you, ma'am. Thank you.
hello.
Ha,
Hello.
ma'am, we are there. Yes, you can ask question.
मैम एक्चुअली ना जो आपने लिंक सेंड किए थे ना लास्ट टाइम जो while we are registering the for the FDP ATAL, so in that there are 3 links are there, am I right? So out of that, which link I have to join? The participant register. Hello.
Yes, yes. From your login, ma'am. You have to join from your login. ATAL
My
login.
own login.
Yes, your own login. You have to log in and then click on the assessment tab.
Wait, means which message you already sent now? In that, first one is the register. Am I right? Participants can register this link. This one.
Yeah. So you have to log in
Have you
using your
registered?
login.
Okay. But I don't know.
During the feedback session, we will take a photo of all the participants. हाँ हेलो, एक मिनट, हाँ just a minute.
Yes, sir. Any doubt?
Hello, madam. Hello.
Yes, sir.
Hello.
Yes, sir. So you have to log in from your ATAL login.
Yes, I have ATAL login through ATAL, but when I after start button na, the dialog box is coming. Questions are not submitted.
Sir, go in the assessment tab.
Assessment.
Huh.
Okay.
There you will find the questions.
Okay.
Hello. Hello. Doshi ma'am. Hello.
हाँ सर बोला ना.
We have to take group photo actually.
Yeah, but then it was better we could have taken it first because I doubt how many of them will be joining for the feedback. But then yes, we will ask at the end all of them to put their videos on.
They will join for photo. No problem. It's a very short program.
Pardon?
It's a short program from 7:30 to 8. Okay.
Yeah, I'm
Definitely.
requesting all the participants to be there.
That time at the start we'll take a group photo. Okay, so that is required
Yeah.
for report.
Yeah, yes.
Hello, madam.
Yes,
Hello.
sir.
नाही मॅडम, ते परत तसंच येत आहे ते.
मग तुम्ही तुमच्या लॉगिन मधून केलाय का सर?
हो मॅडम, मी पहिल्यांदा नाही करत. ATAL खूप वेळा केलेत मी. असेसमेंट मध्ये गेलं, त्यामध्ये ती एक लिंक आहे, टेस्ट लिंक. तिथं क्लिक केलं, तिथून येलो एक चौकोन टूल बॉक्स आहे आणि खाली येलो स्टार्ट बटन आहे. स्टार्ट बटन केली की मग ती क्वेश्चन नॉट सबमिटेड म्हणून येतं.
काय सर?
मिळूया, कारण स्टार्ट झालेले, मी हे केलेले, चेक केले, बाकीच्यांचे सुरू झालेले एक्झाम, आणि सेट केलेली एक्झाम, म्हणजे माझ्याकडून सेट केलेली आहे तरी दिसते तिथं.
नाही, मी एक
पण तुम्ही
व्हॉट्सअपला
अजून
हे
एकदा सर रिस्टार्ट करताय का?
हा ठीक आहे, बघतो मी एकदा. ओके.
एकदा चेक
प्लीज
करा,
एकदा बघा.
मग नाही तर बघू आपण काय करता येईल. ठीक आहे.
हा ठीक आहे.
Hello. Hello, Doshi ma'am.
Hello, ma'am.
Yeah, good evening, sir. Sir, I have completed the assessment
Okay.
and submitted the feedback form as well, but
Okay.
I'm not able to download the certificate.
Okay.
Yeah, that particular problem
Basically,
is
after
happening.
submission of test and test marks are visible.
Yeah, test marks are visible.
Okay.
I feel immediately they won't give you the certificate. Once we submit all the feedback and the reports, that time then your certificates will be generated.
No, no.
Yes, ma'am. Same for me.
But on
Certificate,
the
ma'am.
group, someone has already shared the certificate screenshot. They have directly got that certificate. That's why I
no,
was trying.
it is generating. Okay, we have to look into the problem. How
Okay.
much mark you have secured?
Hello.
It is
What is the mark?
Just, ma'am, just a minute. Kale sir, guide them.
What is your mark, ma'am?
It is 2 to 3. 1 minute. I will just check.
Just check your mark.
Yeah, 1 minute. I got 2 questions wrong, sir. It is showing 96.667%.
Okay.
Okay. You are downloading your certificate on mobile or laptop?
On laptop only, sir. I gave the
On
assessment
laptop.
from laptop only.
Change.
So
You
you
should
can
change the
click on
browser.
certificate. You can click on the certificate once again.
Yes, sir.
Just go to the left hand side, click on the certificate.
Yes, sir. I clicked on the certificate. Down they are showing.
No,
Sorry.
select your current FDP semiconductor.
They are already showing, sir. Starts from Jan 19, ends Jan 24. Down it is written semiconductors. And one print
Madam,
side.
click on the download.
Print option is there. You
icon.
can click
Yeah,
on the
sir.
print option.
Yeah. And it is giving a warning that you should request to check your profile details. If it is correct, then download. So I have checked my general details and then clicked on download button.
So
So
your
it is.
profile it is completed.
Yes, sir.
Sir,
Just
I
once
have
again,
also same issue, sir.
you can check once again. If your profile is 100% completed, then there will not be any issue to download your certificate. It is easily downloadable.
I also have the same issue, sir. Hello.
Don't worry. After some time, you can log in once again. Yeah. Otherwise, what you can do? Log out one time, log in again, and just after
Okay,
login, you can click on the
Yes, sir.
certificate
Now
and
it got
download.
down. For me, Vrishali Badukle, I got my certificate downloaded, sir, this time.
Okay.
Yes. If
Sir,
you have problem,
I just
if you have
request
problem, then
participants
you can
to
log
complete
out
the test
first
first.
and then once again log in.
Okay.
Try to
Sir,
complete the test first.
previously it was showing application number, date, and everything. Now it is showing no FDP approved. Why it is so?
Now you have completed.
Sir, my quiz is not getting submitted, sir. 4 times I did.
Hello.
Test is not submitted.
Yes, sir. 4 times means it is when I click 30th question, save and next, it is telling confirm submission of exam. When I click yes, it is showing some cross in the bottom, sir.
Maybe some because there is other no issue, maybe connection
issue
issues.
will be
Just
there.
try out for because other people have got the certificate. That means procedure has no problem.
No, sir, not certificate, sir. My test is not getting submitted, sir.
Okay.
You can, sir.
4 times I did.
Once again, you can check your net speed. Okay.
Net.
Maybe
Net speed
you
is
have
good, sir.
some net issue.
No, sir. Net. See, now it is telling. I do not know what it is telling, sir. See, now it is showing all 30 questions. Sir, all 30 questions is showing green, right? So now time left 25 minutes. I am clicking submit button. It is asking confirmation of assessment submission, confirmation to submit exam, yes and no. So I should click yes, right, sir?
Yes.
So I'm clicking yes now. So that circle is moving.
Okay.
To now let us wait. Circle is moving. Then after moving, it is showing cross at the down with no comments.
Sir, I got the same problem.
Hello.
And participant FDP marks are not visible to me.
तुला हे पाठवतो डिटेल्स पाठवतो त्याचे ग्रुपला आहे ना.
Maybe on ATAL portal there will be some issue, so you log out from ATAL portal and once again log in, or if you get the same issue then wait for some time, again you can try.
I have sent a snapshot of what is happening. If the cross comes again, I'll send a snapshot, sir.
Don't worry, if you have attended the FDP regularly and if you have doing the test, then certificate will be generated. Definitely it will take some time, but it will be generated.
That's what first submit the test.
Sir, I have log out and log in again, but now in the certificate section, it is showing no FTP eligible for certificate. Why it is so? Marks are
This
also
is
displayed.
portal problem. No, don't worry, ma'am. It is portal problem. So you log out first of all, then
I have log out and I have log in again, but still it is
Sir,
showing the same.
sir, will I have to give the test
Then-
again, sir?
you can wait for some time. It will be
Check the
downloaded.
connection or try to connect other that is internet source. Okay. Try for
No,
that.
sir, my Wi-Fi is strong, sir, at home.
Okay.
No, the ATAL portal issue. Don't worry. You will get your certificate after some time.
Sir, I'll put the snapshot. Can you please have a look at it, sir?
Okay, sir.
Yes, it is showing some.
Unmuted है. Result किती आलं तुझं? हा? 100%.
Okay.
Sir, then now it is not getting submitted, so I should still fill feedback form.
Hello.
You
Yes,
can
sir.
fill your feedback form and your name, participant ID, you can WhatsApp to Parkale sir.
That is okay, sir. But now how to come out of the screen, sir? Because on the once the test screen is there, it will not allow me to go to ATAL website, na, sir?
You can click on ESC button, escape button, you can click.
Okay, fine.
हाँ.
Yes, sir.
Hello, sir.
Hello.
Yes, sir. This is Sonali. Actually, I also tried 3-4 times, but still my certificate is not generated.
Just there is a heavy workload right now on that because there are so many FDP they are completing today. Okay.
Okay.
So on tomorrow it will get download. Okay, I
Okay.
will just put the message. Okay, try on tomorrow, and still if there is any problem, we'll see. Okay.
Okay, sir. Then can I submit my feedback on portal?
Yes, no problem.
Okay, sir. Thank
Sir,
you.
good evening. Hello. Sir, good evening.
Good evening, sir.
I am Dr. Gule.
Okay, sir.
Actually, I did everything from mobile phone. So 30 questions I have attempted all came in a green mark.
Okay.
Where in a mobile, the screen was not moving and I did not find anywhere submit tab.
Yes.
And
Actually, if you try on laptop, that's actually good.
yeah.
Just given the
Anyway,
instruction also.
it's not a problem, sir. I am not much, if I get certificate, it is okay.
No.
Even
You
if
will
not,
get
it is also
certificate
okay.
definitely, but
Okay.
maybe there are internet issues only,
No,
or
it's
other
okay.
issues that are that is portal is heavily loaded right now.
Maybe. For me, important was to get the knowledge, and really the session, all sessions were very good.
Okay, thank you, sir.
And we really came to know that how, the people working in industries,
Yeah.
really they are working, very hard, and it's really good for academician to arrange such kind of workshop. So I congratulate all of you. And it's hardly matter for me to, if
No,
I
sir.
get
We
certificate
will
or not.
solve this problem also.
Yeah. Okay. Sure.
It will be very helpful if you attend our feedback session at 7:30. Okay.
7:30. Yeah. Okay.
7:30
Fine.
in 10 minutes. Okay.
Yeah. Okay. I will log in. Yeah.
Okay, sir. Thank you, sir.
Thank you.
We'll solve. Just put all details to me. Okay, on WhatsApp
Okay.
or email. We'll see.
Huh.
Solve this.
Yeah. Okay. Thank you.
Hello.
Hello, sir. Hello. Hello, sir. Hello.
Hello. Hello, ma'am.
Yes, sir. Actually, now the portal is very slow,
Okay.
so I cannot able to log in and give the feedback.
No problem. You have submitted the test.
Yes, I have submitted
Okay.
test.
No
I
problem.
saw
You
the
submit the
result.
feedback, and then your certificate will be generated. No problem. So that is what the issue right now facing everybody. Okay.
Okay.
So first submit the
If
test.
yes, test is completed, result is shown,
Okay.
but I could not completed the feedback, and I have not generated the certificate.
Okay.
Hello.
No problem. You
So,
try after some time
okay.
today or otherwise at tomorrow morning. Okay.
Okay.
Hello.
That means tomorrow is also okay to submit the feedback.
Yeah, no problem. It's for your
Correct, sir.
both of us. You are not going to get the certificate only.
Hello.
Parkale, sir.
Hello.
Okay, sir.
Just a
Thank you.
minute. Just a minute.
Parkale, sir.
एक
Hello.
मिनिट सर एक कॉलवर आहे एक क्वेरी आहे हा मॅडम बोला
Sir, test is not getting submitted. It's showing the error in a portal. So what to do?
हो
Hello?
सेव्ह नाही होणार ते कसं सबमिट झालं तर सेव्ह होणार
feedback केले
नाही नाही तसं ऑटोमॅटिक नाही होणार बहुतेक सर ते सबमिट केलं. पण ठीक आहे बघा मॅम एक परत करून बघा होतंय का. ठीक आहे बघू काय करता येते.
हॅलो प्रकाश सर.
ओके 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 मॅम ठीक आहे बघू. हॅलो हां
हा प्रकाश सर चव्हाण सर बोलतोय.
हां बोला ना सर.
हा फॉर्म म्हणजे क्वेश्चन्स वगैरे सगळे सबमिट झालेले आहेत. स्कोर
ओके
सुद्धा आलेला आहे.
ओके
फीडबॅक फॉर्म भरलेला आहे.
ओके सर्टिफिकेट
हा फक्त सर्टिफिकेट जनरेट झालेलं नाही.
नाहीये. हो होईल ते परत होईल उशिरा होईल किंवा सकाळी होईल
ओके ओके बाकी सगळ्या ऍक्टिव्हिटीज पूर्ण झालेल्या आहेत आपल्या.
ओके 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 सर.
हा हा ठीक आहे सर.
Attend the feedback session also and give the feedback. Okay.
ओके ओके यस 100% सर.
Thank you. Thank you.
ओके.
Hello, sir.
Hello.
Sir, while after submitting the feedback, I go to certificate and then it is buffering that this is not certificate is not being generated, sir. And
Take some
like
time. Okay. Try after some time. Okay. Today or
okay,
on tomorrow morning you should try. Okay. It get download.
okay, okay.
Hello.
Hello.
Ha, sir. I'm also getting the same problem. I'm not able to submit the feedback because
Okay. Not able to submit the feedback. Okay. Submit it
feedback.
after some time. Try after some time, maybe half an hour.
Yes, I
Okay.
have done with the test
Okay.
and got 90%. So
Very good.
only
Very good.
problem is with the feedback.
Feedback only. No problem, ma'am. Once it is submitted, your certificate will be generated.
Yes.
Okay.
Thank you.
Just attend the feedback session that will start within 5 minutes. Okay.
For sure.
Okay. Thank you. हॅलो हॅलो हा मॅडम काय एकदा क्वेरी सॉल्व्ह करून कंटाळलो. बरं ते सरांना कॉल कर. ओके.
Sir, Hello, sir.
Yes, sir. Yes, sir. Harish, sir.
Yes,
Yes, sir.
madam. Actually, my feedback has been submitted, but my assessment test link is disabled because it was not getting submitted. I attempted all 30 questions. I have also recorded the screenshot of my screen also. So
Kale, sir, are you there?
without assessment, I will not get FDP certificate. If you can get the link activated, I can try again to answer all the questions, madam.
Hello, sir.
Yes, sir.
A link cannot be activated actually. Okay, so you just send me the details and your screenshots. Okay, on my WhatsApp.
Okay, sir. So is this Dr. Parkale?
Yes, sir. Yes, sir.
Okay, sir. No problem. I have
Hello?
recorded snap. Yeah.
Hello?
Hello.
Hello?
You are audible, ma'am.
Madam, same problem is arise with me. Even I tried to submit it many times, but the submission button was not showing the error over there. And now the assessment link is inactive.
Are you using mobile? Are you using mobile for test?
No, right now I am for Zoom. I am using mobile phone, but test I have given from the laptop.
Okay. Now it will get close actually at 7:30.
Sir, but since last half an hour I am trying to submit it, but it is unable to submit.
Okay.
It is continuously showing the error. Even I had shared the screenshot
Keep
in
the
this group on
screenshots.
WhatsApp group also. I
Okay,
tried
no.
it many times for submission. It was showing an error while submitting the
Send the details
button.
to me. Okay.
And
Hello, ma'am.
submit button was active. It is asking for the question yes or no. I click on yes, but after that it is continuously showing an error. And
Correct, correct.
now I log out from
Parkale,
it
sir.
and log in.
Parkai sir, what you do is you put it in chat. Okay, those who are not able to download their certificates can contact you personally one to one so that you will resolve their issues.
Correct, correct. Correct.
You put it in chat so that all the faculties who are not able to download, they will communicate with you tomorrow.
Madam, but this is, I mean, certificate.
You
I
will
know
get, don't
knowledge is
worry,
important.
ma'am. Yeah, Deepali ma'am, don't worry. You will get the certificates. We'll resolve it.
Okay. Okay.
Yeah, because few of the staff members, they are communicating with us. So I felt it's better, like we'll put it on the chat bot indirectly so that then one to one, the staff members who are not able to download can communicate. Hello, all the participants. I feel you enjoyed the session. So it's time for the valedictory function, which will start with the feedback. Yes, hello, Principal Sir. I appeal the participants to give the feedback, please. Can I request Principal RIET Greater Noida to start with the feedback?
Hello.
Yes, sir.
Hello, ma'am. Good evening.
Good
It's a
evening, a
nice,
very good evening.
it's a very nice session, and I just learn much more because my field is not the BLSI, but I just learn a lots of the things. Still, a lots of the things is going on in the BLSI, and whatever the speakers are there, they are a very, very renowned persons, and they just having more expertise in their field. And when I just learn that thing, I just collect all kind of the data, and hopefully I just provided that thing to my students also, so that they just
Are
become
so nice.
benefited in that. But I just have a little request to you, because this time you just cover the advanced semiconductor and the bill assign and all that. Kindly in the coming future, you can arrange a 1 6 day FDP in the communication or the some microstatement and all that, because this is also very dominating field right now, because everything is depending on the antenna communication. So it's my small request, if it is has to be covered, and in that you just cover the CST and the FHSS and all that software, which is very useful on today's designing in the microstrip antenna and all that. It's my small request, if it is possible then.
Yes, sir.
Thank you
Sure,
very
sir.
much.
We'll try to give that. Thank you for the valuable feedback, sir. Any
Thank
suggestions also will be welcome,
Oh,
sir.
and your team is very supporting, and no kind of problem I'm just facing. So that's why I just say, okay, just keep it on, and in future you just arrange such a nice FDP and all kind of and different subject, and you just cover. And I am really proud to be connect again and again.
Yes, sir. Thank you, sir.
Thank you, thank you, thank you, thank you, thank you.
Hello.
Yes, Dr. Gule. Waiting for your valuable feedback.
Good evening, everybody.
Yes,
Hello.
sir. Very
Am I
good
audible?
evening.
Yeah.
Yes, sir, you are.
Actually, it's very wonderful sessions you all have organized. So let me congratulate you all. First, your team, Dr. Vijay Parkale sir, Dr. Neeta Doshi, and all associated members. You have taken really a lot of efforts to organize this, because it is very rare to get such a eminent personality. Means I would like to urge all the young generation that if they are going for a PhD and they are searching for PhD guide, you will not find a better people than this. So they should collect the contacts, and these people are really working in the industry, and it is always better for our academician to have such kind of a connectivity. So really I appreciate and I enjoyed more, because right now I am heading the VLSI department only at Dr. Vittal Rao Vikhe Patil College of Engineering. And most of the sessions where belongs to our field only, like CMOS, VLSI design, FPGA design, chip designing and all that. So really I enjoyed it. And I congratulate once again to all of you. 10 out of 10 to all of you. Thank you very much.
Thank you. Thanks a lot, sir. Yes. Any more feedback, please?
Hello.
Yes, yes.
Huh, ma'am. Am I audible?
Yes, you are. You are. Yes, Dr.
Oh,
Chaitrali.
yes, ma'am. Ma'am, I'm Dr. Chaitrali. I'm head CSC AML department, and I belong to a college in Navi Mumbai, Lokmanya Tilak Engineering College. And this is not actually my field, but artificial intelligence, it has the overlap with almost all the sectors. So I was interested. and I must congratulate each one of you, you as well as Yuvraj sir, for having such a good session. That theme and all the lectures, they were so well organized. The resource persons, they were very expert session conductors. They were on time. All the sessions they started, execution was so well and very effective management, because I have also conducted such FDP recently, and I know how much efforts the coordinators they have to take in this, because it is not at all easy after college hours in the evening to conduct all this and be attentive and coordinate well, and ensure that everything is happening seamlessly. So that was very well done, and due to that, participants like ours, they were very happy to have such contents, as well as communication was very effective in WhatsApp group, on mail, etc. Everything. So I congratulate you, and I wish that you can have such many more FDPs or conferences, etc. to come. So all the best to your team. Thank you very much.
I'm sure. With the support of all the participants, I'm really glad to get very positive feedbacks, and with the energy and
Thank you.
motivation, we surely will go for many other FDPs in which you are always welcome in that
Yes,
also.
sure.
Thank you.
Yes, ma'am.
Thank
Okay.
you.
Thank you very much. Okay.
Thank you. All of
Madam,
you, please be there, because we want to have a.
ma'am,
Yes, pardon?
one more
Yes, sir.
suggestion from my side.
Yes, sir.
If possible on Saturday, please try to avoid 3 session plus valedictory next time.
No, sir, it was the protocol of ATAL FDP.
Okay.
So we
Is
had
it,
to do that. Like, we cannot
uh,
skip the protocol which they have asked us
okay,
for.
okay. If we'll
Even
arrange
we
at
were
a
feeling
college
that.
level, please do take care
Yeah.
of arranging such seminars. Okay, thank you.
Thank you, sir.
I just welcome our principal, sir, Dr. Shailendra Kumar Mukune, sir. They have also joined the session. Welcome, sir.
Thank you, Parkay, sir.
The feedback session, and we are getting the feedbacks from all the esteemed participants now, sir. So you can also. Yes, sir.
Yeah, I'm listening to their feedback.
Oh, okay, sir. Nice. Yes, may I request any more participants to please give the feedback on the FDP?
Hello, ma'am.
Yes, welcome, Swati ma'am.
Yes, ma'am. Thank you
You're
for
audible.
this FDP. I extend my heartfelt gratitude to SVPM's College of Engineering for hosting this remarkable 6 days ATAL faculty FDP on advancement in semiconductor technology trends, application, and future perspective. It is a matter of great pride to be a part of this knowledge sharing initiative. A special note of appreciation to Dr. Yuvraj Parkare sir and Dr. Neeta Doshi ma'am for their perfect planning, seamless execution, and tireless dedication in making this FDP a grand success. Their vision and dedication have provided us with a platform to learn from the very best in the VLSI domain. This FDP has been a journey of inspiration and learning. I'm an alumnus of SVPM. So as an alumnus of SVPM College of Engineering, I'm especially proud to see how our institution continues to foster academic excellence and industry academic collaboration. I would like to thank all the resource person. Especially, I would like to recognize the alumni of SVPM's College of Engineering who contributed as speakers. Your presence not only elevated the quality of FDP but also inspired current and future students of our alma mater. Your living example of how strong academic roots can lead to global professional excellence. So, to the entire organizing team, technical supporting, and thank you for seamless execution. This FDP not only enhanced our technical knowledge but also strengthened our bond with SVPM's College of Engineering. So, thank you, Parkare sir. Thank you, Doshi ma'am, once again for making this possible. So, we look forward to many more such enriching initiatives from our beloved institution. Thank you, ma'am. Thank you for such a wonderful FDP.
Swati ma'am, for that. Like even really, like we are very fortunate ki the alumni which were their contribution, really they are the assets of our college. So hats off to all the participants and especially the esteemed speakers who shared their knowledge, because we as an academia were lagging in the expertise which they had from the industry. So they bridged the gap. Thank you, Swati ma'am.
Yes, ma'am. Yes, ma'am.
Yes, any more participants? Hello. I'll just check the list who are present.
Good evening.
Yes. Yes, Deepali ma'am.
हाँ मैम हाँ दीपाली मंगेश काले सिद्धांत कॉलेज ऑफ इंजिनियरिंग सुदुमरे ma'am this FDP is so limited. That means all speakers explain the different topics regarding current technologies, and this FDP also helpful for PhD research also. Thank you ma'am for organizing such wonderful FDP.
Thank you ma'am for the feedback.
Okay ma'am.
Yes, thank you Rushali ma'am for the feedback in the chat. I'll just read it for all. Thank you so much for all your efforts to make this FDP program a great success. Very good and intelligent speakers were brought in into the platform to guide us through this topic of semiconductor. Very nicely managed and communicated through. Thank you, Vrushali ma'am. Any more feedbacks, please? One more feedback in the chat. It is from Mrs. Gausia. You could have unmuted and given this wonderful feedback. We could have loved you. Okay, I can read it. Sincerely
Definitely,
thank
ma'am.
organizers.
Good evening, ma'am. Hello, hi, ma'am.
Yes.
It's been a pleasure seeing you. I really, like more than the SAP, I really admired the way you have handled everything. It's really amazing, ma'am.
Thank you.
I sincerely thank the organizers for conducting such a wonderful, well-structured, and giving us this wonderful FDP program. The session on advancement in semiconductor technology was beyond the academics. What we have seen and what we have learned is completely different of realizing and facing all the issues and what all development we can make it. I'm thankful and grateful for the opportunity to learn and update my knowledge. I sincerely thank all the speakers for their insightful session and for sharing their valuable knowledge, because we can hardly find such a wonderful speakers to see and to share their expertise. That was really amazing. And I also thank all the speakers for their valuable time and insights and engaging session. And I also thank all the participants. They were really engaging and also
Yes.
created a curiosity to ask questions, to learn more. That was a thing. Like in many of the FDPs, we hardly see the participants just listening. Here, I found another thing that the participants, like me as well, was very curious to know what sort of questions can also be raised. So that was really amazing. And looking at you always, these 6 days were really amazing, ma'am. Thank you so much. Thank you.
Thank you so much.
I am from Karnataka, ma'am, from Ballari Institute of Technology and Management.
So nice,
This is the
so nice. So this was
Looking for-
pan-India participation. Thank you for that. Wonderful
Thank you,
feedback,
ma'am.
ma'am.
Thank you, ma'am. Looking ahead for many more sessions from your side, ma'am.
Yeah. You can also arrange. We'll be participants for the programs if you arrange.
Definitely, ma'am. Thank you so much. We would definitely have a link with you, ma'am, always.
Sure. We'll be in a network. We'll be in touch.
Yeah, definitely, ma'am. Thank you so much, ma'am. Thank you.
Thank you for the feedback.
Thank you, ma'am.
Swamini ma'am has also given. It's really nice execution for the program and it's very useful. Then Sumit Kumar has also given. Thank you for organizing the FDP, very systematic delivery of lectures. Thank you, sir. We could have loved you hearing by unmuting. So at least 40 participants are there. What we can do is, sir, we can on our videos and take a click video. Yes, it's a request for all the participants to make on the video. Yes, Pranali Deshmukh has given. Thank you so much for all your efforts to make this FDP program a great success. Very nicely managed and communicated FDP. Thank you.
Hello,
Rushali
ma'am.
ma'am, also thank you. Yes,
Hello, ma'am.
Anu
Can you hear
Chalan.
me? Yeah,
Yes,
yeah.
yes, you're audible.
I'm from Amrita School of Engineering, Amardapuri campus from Kerala. So this was a very nice session. All this, I am also from VLSI. So I'm pursuing my PhD also, but I am doing in material science. So this was a nice session and it's very well structured. Even if it was difficult to after classes to do these courses, but it was very really nice sessions.
Thank you so much, Anu ma'am, for initiating. So many participants are eager to give the feedback. This is the best part of the FDP, I suppose. Otherwise, we have to plan and tell them and all that. But this is very insightful, ma'am. Thank you for motivating and inspiring us.
Thank you, ma'am.
So can we all make our videos on so that we can have a click? Because that is required for FDP for us to submit as evidence.
I request all the participants to turn on the cameras. There are 40 participants. Just a minute. Okay, good. Okay, thank you. Thank you to all. Okay. Ma'am, please invite Mukune sir to address the participant.
Feedback?
Hello.
Any more feedbacks, please? Okay, then without I know this
One of
Saturday
the
was
speaker
really.
is also present over there. Dr. Pranav Pawar is also present.
Yes.
So
Hats
even
off.
you can take the feedback from them also.
Okay, so may I request our principal Mukne sir to give vote of thanks and express his views?
Okay.
Over to you, Mukne sir.
Thank you, madam, for inviting me for this validatory function. So first of all, let me express my sincere gratitude for all the experts who delivered sessions, and by listening to the feedback of the participants, I think these sessions were really wonderful, fruitful, and it will help in their career to excel in this particular semiconductor technology area, advancements in semiconductor technology area. So I was listening to the participants. One participant from Greater Noida, Principal Sir. Then resource person Pawar Sir also present for this valedictory function. And our alumni Deshmukh Madam. Then other participants who have expressed their feedback. And one thing is, it is very important that learning takes place, means it continues. It should not be stopped. We should always learn, and learning happens through this particular such faculty development programs. Otherwise, in our routine day, we used to take lecture, practical, whatever load it is given to us, and we restricted to that only. But such faculty development program gives us opportunity to learn beyond our subject topics, to new things, upcoming technologies, and for that purpose, I means really thank AICT ATAL for taking such a wonderful initiative, and for funding also, for granting some funds for conduction of this particular ATAL FDP. So on behalf of SVPM College of Engineering, once again I thanks. And what do you say? One very important thing is that our coordinators, Dr. Yuvraj Parkale sir and Dr. Neeta Doshi madam, and support team, Mr. Dahale and others. So really they worked very hard to make this FDP successful one. Thank you, ma'am.
Okay.
Thank you, Parkale.
So,
Thank you, sir.
thank you, sir, for your valuable feedback and the energy always we gain from you, the motivation we gain to conduct like this kind of platform and the FDPs. So, Parkay, sir, should I go for vote of thanks?
Yes, ma'am. Yes, it's a 7:54.
Yeah, it's already, and the participants are just waiting for that. So, on behalf of the organizing committee, I extend my sincere gratitude to AICT and the ATAL Academy for providing this prestigious platform that continuously strengthens faculty competence and research excellence. We are deeply thankful to our esteemed speakers and the guest of honors, especially many of them were our alumni. So hats off again to all our alumni who has made us really proud of whatever expertise you have shared with us. Whose rich expertise, global exposure, and inspiring interactions made this faculty intellectually rewarding. Their willingness to share knowledge, industry insights, and future research directions truly elevated the quality of the program. I express my heartfelt thanks to the SVPM management for their constant encouragement, strategic support, and vision in promoting academic excellence. I am sincerely grateful to our Honorable Secretary for his guidance and unwavering support throughout the program. My respectful thanks to the principal for academic leadership, motivation, and institutional backing that ensured smooth execution of this PDF. FBD. I acknowledge the dedicated efforts of all the faculty members and the coordinators whose teamwork and commitment made this program a success. And special appreciation to the organizing team for meticulous planning and flawless coordination. And not least but last, I thank all the participants for their enthusiastic involvement and active engagement, and especially the feedback also, and the questions which made the sessions interactive and interesting during the sessions. So once again, I express my heartfelt gratitude to everyone who contributed to making this ATAL FDP a memorable and impactful academic experience. Thank you once again to all of you for being there with us to make this program a good success. And I hope we will continue this learning back again. Thank you. Parkare sir.
Okay, thank you, ma'am. Thank you, Mukune sir, for coming for this valedictory section, and also for supporting for this FDP and guiding for different procedures, that is for FDP registration to report submission also. I also thank to all the participants
And we are getting all the feedbacks now in the chat box. I could have, like, we could have loved you hearing, but okay, you are given a good feedback. You have motivated us. So let's keep this learning, lifelong learning. And with this, and if you have any doubts regarding the certifications, you can communicate with us. We'll try to resolve it. Be assured about that. Just we'll see what actually has happened and we'll resolve it. So thank you once and all to you, all the participants and all the speakers, especially again. Thank you once again. So shall we call this a day? And of the end of this FDP.
3 minutes we will wait. Okay. It's 8 o'clock.
Thank you.
We'll close.
Okay, sir.
Thank you, sir. Mukni sir, thank you. Thank you.
Yes, yes, sure, sure. All the participants, whatever feedback you are giving, we'll be working on that and let's meet for the next FDP with the same enthusiasm. Chalo. Good night, everyone.
Query